for this again.
This is awesome. All right. So say hello to everyone.
Hello, everybody.
Wow.
Well, I think there is more and more people who is joining the group. So I say hello to everybody. Be welcome. And again, we have the hello from everywhere in the world in the chat. You can look at the chat. This is just incredible. I love that.
Yes, I think it's fun to look at this. So far, we've got Myanmar and Lima, Peru, and Rhode Island. Oh, that's a wonderful place. I had so much fun in Rhode Island one time. Germany, Pakistan, Paris, Albuquerque, and my home state of New Mexico. Well, not my home state, but where I live. Spain, Southern Oregon, Quebec, Cornwall, France. Would be
Hey, Greg. Ron D'Elio, hello again. Nice to see you here.
Olivier Gard. You know, I'm not sure that Olivier gets enough credit, but I have to tell everyone that Olivier has been very instrumental in the success of this workshop. Without Olivier's help and participation and endless support, it probably wouldn't have happened, and it certainly wouldn't be as good. Olivier Gard is a wonderful resource to the amateur spectroscopy community, and if we were all in the room together right now, we could give him a big round of applause. But anyway, just know that Olivier is not only a great resource, but he's a great person. So we're really lucky to have him participating.
Thank you, Ken.
You're welcome.
I have to say that everyone in our community is a wonderful individual and a very wise person. We're learning together. So this is one of the things that I've been enjoying in this conference. I have to tell you, I've been learning new things. It's actually wonderful. I love learning new things. So thank you all for participating. Thank you all for contributing. Thank you all for discussing. And thank you all for being patient with each other while we're learning. It's important.
Okay, so we still wait for 1 or 2 minutes for the newcomers.
Yeah, let's do that.
And we will start. I like the comments on the chat. You are all super giant of amateur astronomy. Thank you all. Well, there is some snow in Canada.
So while we're waiting for people to settle, have their first, second, or third cup of coffee or tea of the day, just plugging in. Don't forget to send your spectra to the AAVSO Spectroscopy database. I'm really looking forward. I'm hoping that after this workshop, we'll start seeing more and more spectra coming through. It's a wonderful repository of a lot of great information that is being used for science. So for research projects, for papers, for student projects, for anyone who wants to do a project actually. So an encouragement for all of you.
That's perfect.
And we're here to help, right? Yes, sorry. All yours.
Yeah. So let's go. Let's go. So hello to everybody for this this last day, the fourth day of this workshop about spectroscopy from the AAVSO. Again, this is a pleasure to see all your names and all your messages in the chat. So this fourth day is dedicated to the software tools. And so you remember the first one was for the beginners. The second one was regarding all the program observation programs we can have. And yesterday it was about hardware, the different instruments we were available. And now we'll talk about software. And you have seen that for every day, we wanted to start by an astrophysicist talk to be sure that we first talk about what we can do with our instrument. And again, we are not taking spectra just for spectra, we are taking spectra to do science and to better the universe we are in. And I think it's important to have this this view on the science by people who are really able to do it. And today I'm very happy to welcome and to introduce Katherine Blundell. So Katherine, you're working at the University of Oxford in UK. And well, we met the first time, it was a few years ago at La Rochelle, where you gave a talk that was excellent, and you were talking about SS433, if I remember, and the micro quasars. And so I'm always impressed by your energy and what you are explaining. After we hear you, I feel more intelligent. So I'm very happy that you you can talk together. You can talk today. Sorry. And well, by the way, we work together within Cheliac about some instruments and especially some systems to have double fiber systems to take the sky background at the same time of the target and so on for your own instruments. So we work a little bit together. And I also know that you work very often with Steve Lee in Australia. Well, that's it. And now I'll let you take the mic. Regarding the from tactical things, people can ask questions by the Q&A tool from Zoom. And if you agree, I will look at this Q&A system. And if I see that there are urgent questions, I will interrupt you. But most of the time, all the general questions will be kept for the end of your talk. Okay?
That sounds
so,
good.
Thank you. Thank you very much.
Thank you, Francois, and greetings to you again. It's very good to be in contact with you following the work that you've mentioned, and greetings everybody all over the world. What a treat it is to be able to get together and talk about interesting things like spectroscopy. I hope, Francois, are you able to confirm that you can see
Yep.
my slides okay?
Yes, there is. Yes.
I can hear a little background noise. I don't know where that's coming from.
So yes, please, everybody, if you can mute your mic, and I will do mine.
So the title of my talk today is The Beauty and Science of Spectroscopy. I think there are many fans of spectroscopy who are here participating in our joint meeting. I think many people the world over love rainbows, and the particular circular rainbow that I'm showing here is formed when we disperse white lights, white light from the sun via the water droplets in a cloud. And when I woke up on a flight to the Rainbow Nation on this particular South African Airlines flight, it was such a treat to be able to capture this particular circular rainbow. None of the rainbows and none of the spectra that I'm going to be talking about today are circular, but I do contend that they are every bit as beautiful as this first one that I'm starting my talk with. So I'm going to be talking about galactic objects, and I'm going to be focusing most particularly on an object that Francois knows that I have worked on for very many years. It's a micro quasar in our own galaxy. It's pretty much, I don't know whether you can see my cursor, but within those red circles, that's where this particular microquasar is located. If you don't know what a microquasar is, let me tell you the brief ingredients. It's got a black hole in the center. It's a binary star system. The black hole is ripping material from the normal star, and in the process of being a particularly messy eater, it is accreting matter in an accretion disk, and it is throwing off matter also via the accretion disk. but also in the form of jets, also via something special called a circumbinary ring, which is outside of the binary star system where all the action is coming from. So in this particular part of the sky here, this photograph that I'm showing you here is from a digital camera taken when the sky is not like the sky is in Oxford at present, which is that very grey, rainy sort of cloud, which none of us like. But this is a beautiful optical view of the galactic plane. I want to take a brief detour into radio astronomy and show you what happens when we just zoom in and look at the galactic plane. This is rather a scruffy radio image, but here going from lower left to upper right is that same galactic plane. And I want to focus on this particular object here, which is a big nebula called W50. If you take a closer zoom in of this radio structure, this W50 nebula, you'll see that the very central region is remarkably circular. Not that my hand movements with my mouse are circular, but that's formed by a supernova explosion whose expanding circular shell gives rise to that shape. But these elongated features here, this is going head first into the galactic plane, and this side here on the left is going out of the galactic plane. Those are formed by jets. Now, jets are emitted from the vicinity of black holes in microquasars in our galaxy and in big, powerful quasars all across the observable universe. And they're superb fun to study. And I thought if we're talking about the beauty of different stars, then I should surely show you some of these today. This is a picture of the Very Large Array Radio Telescope, which of course starred in the movie Contact with Jodie Foster, although aspects of it were rather misrepresented. Of course, the beauty of radio astronomy is that you can look through the clouds, which is not something we can do as optical astronomers. But let's just take a moment to think of our gratitude to the radio astronomy world and John O'Sullivan in particular from CSIRO in Australia, without whose work in pursuit of signatures of merging black holes in the galaxy, we would probably not be meeting like this today. It's thanks to his work in thinking about interference suppression algorithms that we have the 802.11 protocol, which is the means by which we can connect over Wi-Fi today. So hooray for radio astronomy and hooray for John O'Sullivan and his team in particular. But back to the W50 nebula, which, as I said, is formed, the circular shape is formed by a big supernova remnant, and the ears at the side are formed by jets. I'm showing a zoom in at the bottom here. If I zoom in even further, you can see an image which I made with the Very Large Array Radio Telescope quite some years ago now, with a wavelength of about 6 centimeters. And you can see this remarkable zigzag, curly corkscrew shape just here. If you zoom in even further with the very long baseline array, then you see this amazing jet structure where if we could look in a time-lapse sense, we'd see those blobs of plasma move further and further away from the black hole where they were launched. Unfortunately, the problem with doing successive time-lapse studies with the Very Large Array Radio Telescope is that other radio astronomers want to use the VLA too for their work. But if we could kidnap the Very Large Array Radio Telescope for ourselves, and if we could color code the material coming out of the screen blue and going into the screen away from us red, then this is what we could see if we could do such a time lapse. It's about day 65 now that corresponds to the radio image that I just showed you. What's going on here and why am I trying to hypnotize you? Well, honestly, I'm not trying to hypnotize you, but this cartoon representation here that I just coded up on my computer is a representation of physical reality in our galaxy. Some people find it a little easier to look at this version of that, where pairs of oppositely directed blobs of plasma are launched into space along an axis which successively changes in time. Imagine that you're paddling a kayak. The angle, the orientation that is traced out by your paddle corresponds to the axis along which these oppositely directed pairs of blobs of plasma are squirted in this real physical situation in this beautiful microquasar called SS433. Now, you can't, as I've said, kidnap the Very Large Array Radio Telescope. You can't do any color coding of red and blue, and you can't do time lapse. However, what you can do if you want to study this sort of dynamic is you can take an optical spectrum from this central launch point. And so this spectrum here is exactly what you see if you put an optical fiber on the very central launch point from which those radio jets emanate. What you see here is a strong line corresponding to Balmer H alpha. That's known in the trade as a stationary H alpha, which of course means it's not stationary at all. It wiggles around and it shimmies around according to the processes of accretion and mass loss from the accretion disk from the circumbinary disk. This blue line here, well, this one is called the blue shifted H alpha line. This one here, this is called the red shifted H alpha line. These two are helium. And I've just got labels on those here. Well, so it turns out the fact that we have a red shifted H alpha line and a blue shifted H alpha line, that comes from the Doppler effect, which we've of course heard a lot about. If you take one of the revolting orange sodium streetlights that adorns the streets of Oxford, then you see the particular orange colour that you do because of an electronic transition at about, 5,890 odd angstroms, according to the electronic transitions within the excited sodium atoms. That fingerprint has a very specific set of lines corresponding to it. If we nail such a street lamp on the back of the space shuttle, and skipping over a few technical details here, that space shuttle whooshes away from us, then what is seen as an orange line shifts down towards the red to longer wavelengths. So what might in reality, in the rest frame of the space shuttle, or at least of the street lamp, the orange, gets shifted down towards the red. Now you get moving blue shifting and red shifting lines. This has been known for donkey's years. Early work on the identification of this was done by David Clark and Paul Murden in the late 1970s. Martin Rees and Andy Fabian did quite a lot of work. Such was the excitement of this object, talking about its changing blue shift and its changing red shift. This object appeared on Saturday Night Live towards the end of the 1970s. That's how important it's been in various people's thinking. And so, oh, sorry, I should apologize. Let me just skip through these equations. Such is the importance of this microquasar object and my own research interests in studying how matter is expelled from nearby black holes in response to how matter is attracted towards those same black holes prior to its expulsion. I established a network of telescopes called the Global Jet Watch. It's called global because it comprises a network of telescopes that are globally distributed, separated in longitude. So there's always at least one of them in darkness. And its original purpose in a research sense was to look at microquasar jets. And we absolutely still do that, but our research interests have broadened very much still. So the idea is, if you're studying an object over here in the galaxy, then each of those observatories can take it in turns to look at the object that we're particularly studying. It might be a nova explosion. It might be Eta Carina during its recent periastron. But I'll be talking today about the microquasar SS433. How do you build observatories? Well, a lot of blood, sweat and tears, but eventually, I'm sure many folk here know, the moment you get on sky is a beautiful moment. This is the back end of our telescopes. The telescopes are ARCOS 20-inch telescopes, and we have an imaging camera and filter wheel, and we have this instrument selector, this instrument manifold made by Optech. It's their Perseus, and it's just brilliant for being able to switch between imaging, and Francois Cochard made these fiber injection and guiding units. This is the guider camera here, and slightly out of shot, you can see the optical fibers that go down to the spectrograph, which is on the concrete floor in a minute. This is another view which shows you the back end of our telescope. As I say, the guider and the fiber optic cable that takes the light collected by the telescope down to a spectrograph at the bottom. Our spectrographs are in shiny red boxes, and they were designed by my colleague Steve Lee, who's pictured here on the right. The dispersing element in these spectrographs is a volume phase holographic grating. That means it's got extremely high throughput, which is important for many of the faint targets that we look at in our galaxy. Apart from that particular dispersing element, all of the other elements in our spectrographs are off the shelf. Keen photographers may recognize the 85mm lens that we have here to focus the light dispersed by our volume phase holographic grating. Well, these are our telescopes. We have various auxiliary cameras, and this is the setup that we have. So this is our network topology. All of the observatories are connected to the University of Oxford Department of Physics by some hardware VPN boxes made by the cybersecurity company Sophos, which is based in south of Oxford, in Oxfordshire. And what it means is that every IP device, every PC, every particular different gizmo that we've got in the observatories thinks that it's connected to the University of Oxford Department of Physics via an Ethernet cable that's several thousand kilometers long. This is a movie that I hope will start showing you. It's just a screen capture really of the start of one of our nights of observing. We use the Prism software because it allows you to run a whole bunch of cameras at the same time, not just a science camera and a guider camera. And it's important for a lot of the science that we're doing that we can have multiple cameras. So the camera that you see here is our imaging camera. This one is our guider camera. This one is our spectroscopy science camera. And the two that are about to appear here and here are some of our auxiliary cameras that enable us not just to do time-lapse spectroscopy, but to do time-lapse spectrophotometry. And that turns out to be really important when we're studying particular types of dynamic and explosive events. So the way we operate is that the imaging camera, which is a fairly wide field, takes an image around the target that we want to do spectroscopy on. It does a plate solve, it does a shift, it does an iteration of that process. If we haven't got our target of interest, we're looking at Betelgeuse here, lined up on the fiber optic cable that is part of Cheliak's fiber injection and guiding unit. So we take some spectra here, obviously very, very short because it's Betelgeuse, because it's stupidly bright. And then we rock off to our next target. This is Beta Pic, which, as some folk here may know, is very interesting in terms of its protoplanetary disk. So that's another kind of object that we study. We then repeat and do the same wide field image on about the right place in the sky. We do a plate solve, we do a move so that we're exactly lined up. This is the guider camera here, which does the guiding for us. The guider camera field of view is a bit too small to do that plate solve, which is why we switch between the imaging camera and the guider camera. And it's the Optech people have written brilliantly reliable software, so we can just switch the light path from one port to another. and conduct our observations in this quasi-robotic way. This works beautifully, and we get a lot of data. You can see a bright H-alpha line just there in that particular spectrum. Okay, so PRISM is how we do that, thanks to its facility to allow many multiple cameras in parallel. Well, this is how we operate the global JetWatch observatories. But before I tell you about some of the science that we're doing, I just want to mention to you that by design from the outset, this project is not just about research, it's also about spin-offs. And that's because I want to do my bit to encourage the next generation of young scientists, especially girls, especially from developing countries. So one of our observatories is in rural southern India. It's hosted by a residential school there, which is run and was established by the government of India. So schoolgirls here in the bottom, and our observatory here, and various meteorological monitoring equipment up here. This is inside our observatory at the boarding school in South Africa, the girls' school, which hosts our observatory there. You can see a little bit of our telescope on the right, and you can see the schoolgirls operating the telescope. The paradigm is, before local bedtime, they are free to use the telescope for whatever they want to observe. Jupiter and its moons are a favourite, but all sorts of galaxies and nebulae obviously get a look in as well. Of course, during lockdown, this is massively limited, which is a great pain, but we know lockdown won't last forever. These are some of the girls at the India school, and again, during daytime, just getting to know what different bits of the observatory are for. I have never met in all the world the thirst for knowledge that I have in this particular school in India. Their thirst for knowledge is like nothing I have ever seen. They are so eager to learn about astronomy, about physics, about engineering, about technology. And that for me is every bit as crucial as the data streams of time-lapse spectroscopy, which enable us to study better still how black holes attract and expel matter from nearby their vicinities. This is a time-lapse sequence of photographs, start of night setup, my South Africa school, two girls here, Jenna and Katie. Start of night setup, we all know what it's like. It's a little bit tense. Is the weather going to stay clear? Am I going to remember what I've got to do? But then the moment that you first move the telescope, and then even better, the first time you see your first galaxy, it's a very beautiful moment. Of course, I can't be in several places at once, so Skype or Zoom or WhatsApp is how we keep in touch. And you may indeed recognize these bookshelves, which are these exact same bookshelves in front of which I'm speaking to you now. I'll get back to the science, but first I'm going to share with you an email from one of the students at the India school who went on to study physics with engineering at a college in southern India. Dear Madam, hope you saw the image of Jupiter. It was magnificent. We even saw, and there's a bunch of targets you may know. Guess what, Madam? Each night in my dream, I play only with stars and nebulas. Once I enter the observatory, I forget everything. I feel I have entered heaven. So these school children are experiencing the same joys and struggles that we all experience as we work in our own situations with our own telescopes. And it's a great treat to be able to open the wonderful world of science to those students as well, those constantly replenishing populations of school children. So back to the science and back to this wonderful micro quasar called SS433. I showed you this spectrum earlier, and the point to realize is we've got a blue shifted line and a red shifted line. This is essentially all from just hydrogen. Hydrogen is squirted out towards us and away from us in directions that are changing with respect to our line of sight, such that every time we look at this object, it looks different. And if we stack up all our spectra, we start to see persistent changes over time. These lines arise from the jets, which I showed you in that radio image towards the start of my talk. Why have so many telescopes? It's certainly been a lot of work, but it's embraced a lot of students. But what are the benefits for science? Well, I'm just showing you a pair of spectra here from our observatory in Australia left, Western Australia, as I call it in front of Australians. And what you can see here is the spectrum, all color-coded in blue, was taken 24 hours prior to the spectrum that's color-coded in burgundy. In 24 hours, there are dramatic and significant changes to the spectrum. We're looking at a particular time in the cycling, in the periodicities of this beautiful microquasar, where both the blue shifted line and the red shifted line are both at longer wavelengths than this so-called stationary H-alpha line, which you can see here. But even that's changed in 24 hours. And the changes that go on in this so-called stationary H-alpha line are telling us about changes to do with the accretion disk and the circum-binary disk, which is outside of the binary star system, which comprises the black hole and the star that the black hole is pillaging. So if you only observe once per night, you miss out on a lot of the action. And so anyone who wants to get involved in studying spectroscopy, it can be very enriching to study objects that change. It can be very flummoxing, very baffling, very confusing to do so, but I really recommend that you have some fun with objects like this. Even that stationary H-alpha line has long been known to change in its shape as a result of its orbital period. So the jet lines going backwards and forwards, or the jet axes changing, is something that takes place on timescales of about 6 months. But the stationary H-alpha line also shimmies up and down on timescales of about 13 days. This has been known for a while, but I think it's been misunderstood for a while as well. If you look at these two dynamical situations, let me see if that starts moving. So the one on the left and the one on the right, at low spectral resolution, look to be identical. The one on the right at high resolution is revealed to be a kind of a Doppler effect thing, where you've got two bodies in orbit around one another. At low resolution, if you reduce the resolution to this, it looks qualitatively the same as the set of spectra on the left, all coloured red here. But that corresponds to a completely different dynamical situation, where you've got lots and lots of lines, all at exactly the same wavelength, but changing in intensity. So not a Doppler effect at all. And it's important to be alert to what might I be seeing that isn't revealed at the resolution that I've got, either in terms of spectral resolution or in terms of temporal resolution. And so we have to factor in information at lots of different times to fully sample the phase of the orbital period and at different spectral resolutions, so we fully understand the dynamical picture. So this version on the right is what people thought for some time. We were able to demonstrate that actually it's the dynamical picture on the left. And that dynamical picture arises from what we discovered was a circumbinary disk, outside the binary, therefore stationary in wavelength, but being differently illuminated throughout the orbital period. Hence the intensities of those lines are going up and down throughout the orbital period. So awfully good fun to watch this. If you do deconstruct during nice quiescent times what that stationary H-alpha line is doing, then you get these separate Gaussian components. If you plot those in the graph that I've got on the left, what you see is a pair of these little dotted lines. They're plotted against wavelength. That's the circumbinary lines that I told you about, the ones that are rock steady in wavelength. But that very broad Gaussian that we saw is wiggling around in wavelength as a function of orbital period in response to the fact that that broad line is actually a wind off the accretion disk, which surrounds the black hole, which is itself orbiting around the normal star that the black hole is ripping to bits. So very exciting to study this stationary line at the same time as studying those moving lines. And the combination of these together means that we can look at the cause and effect processes of matter being attracted towards the black hole, matter orbiting around the black hole, and matter spat out away from the black hole. What I've done here is to do a stack of a great many spectra throughout just about an orbital period. This bright yellow streak that's going up, so the time, the vertical axis here is time. This is abbreviated JD, Julian day, and across the horizontal axis is wavelength. So you can see, I hope, the stationary H alpha line there very clearly. You can get a sense of motions within it, but it's nothing compared with how the other lines move around, corresponding to the precessing axes of the jets, which were squirting out that blue and red toothpaste I showed in my cartoon movie earlier on. Well, if I just zoom in closer, this green streak here is just a zoom in, still with time on the vertical axis, but that is the stationary H alpha line. You can see why I was sniffy earlier about the idea that this could be called stationary. There's matter streaming off to the left and to the right. This may be a slightly clearer visualization of what I've just showed you. Again, we've got the jet lines changing backwards and forwards in wavelength. Whoops, sorry, let me just go back. And you can see matter streaming off from this central point. So those purple dots right at the center, that's the circumbinary line steady in wavelength. But it's actually the accretion disk, the accreting material, that's separating away from that central line. It separates further in wavelength because it's getting faster. That's a process that happens when it spirals further and further in. And guess what? That corresponds to when the jets are faster than normal and more intense than normal. So we're beginning to tie down some of the cause and effect processes that govern accretion and jet launch. Now, my next slide is for people who are just a little bit interested in equations. If equations aren't your thing, stay with me. This is only one slide. But I just want to give a sense of how you can turn a single spectrum of this beautiful microquasar into a speedometer. All you do is measure the wavelength of your blue shifted jet lines and the wavelength of your red shifted lines into a red shift, which we'll call Z plus, and a blue shift, which we'll call Z minus. If you put these values are defined by a model which was developed long time ago in terms of the speed at which the jet material is moving, beta, which is the speed in units of the speed of light, theta is that precession cone that's being traced out, I is the angle of inclination that it's coming out of the plane of the sky at you, the symmetry axis of that precession cone, and phi here is just a phase around that cycle. Now, if you add these two equations together, then you get something that just depends on this factor gamma. If you haven't met gamma, let me introduce you. This is the Lorentz factor, which you can trivially turn back into the speed beta. The speed beta is one of the properties we really want to know. We want to know how fast is that material launched from the black hole. And the answer is given by something, there are ones and there are square roots and different exponents, but all you do is add together the simultaneously measured redshift and blue shift from a single spectrum, and you have got the launch speed on that particular night or at that particular epoch. A few hours later, it'll be different. That speed changes between 20% and over 30% of the speed of light. We can measure it. We have turned a spectrograph into a speedometer. There are some slightly different equations. I won't inflict them on you now, where you basically difference the top two equations, and that gives you the angle of launch of the plasma from nearby the black hole. If you've got the speed and you've got the angle, you've got the velocity vector, you are in business to be able to understand and quantify the dynamics of how plasma is ejected from away from nearby a black hole. This is something that's really important if you care about how jets are launched from the big, powerful quasars in the extragalactic universe. Okay, well, here is a collection, again, of just a stack of just a couple of years worth of spectra that we've been collecting. If I take those spectra that I showed in my previous couple of slides, and if I apply the equations that I showed you 3 slides ago that turn a spectrograph into a speedometer, and if I apply the other equations that I didn't show you that give me the angle of launch, then I can predict the trajectory of what the jet trace of launched plasma from nearby the black hole would be and make a prediction. Now, unlike a radio telescope, I absolutely can color code the information with what's coming out of the screen at you blue and going into your screen red. I can do that because I know what the angles are, because I can calculate them from my successive spectra. And so I can make a prediction for what the jet trace ought to look like on a particular day. As time goes by, the launch material will expand out and move further and further apart. But on a given day, I can say, if my equations are correct, if my spectroscopy is correct, if my wavelength calibration is correct, this is what that jet ought to look like. This is my prediction. What do we do with predictions in science? We verify them by further observation. So I made a prediction of what this jet should look like on a particular date to use together with a radio telescope at the Chatnantor Desert in northern Chile. We had been awarded very competitive observing time on the ALMA telescope, but in fact, just 2 weeks before our observations, a massive earthquake hit. The epicenter wasn't nearby the ALMA telescope. In fact, it was just 40 kilometers from my school observatory in Chile. Quite a lot of damage was done. We kept going with the other telescopes, and the ALMA telescope kept going. And so we were able to make a radio image on a particular date. I think it was the 25th of September. And we were able to overlay the radio image from this telescope on my prediction. And this is the prediction. This is the radio image. So this vindicates the use of those experiments, the use of those equations, and this particular use of this time-lapse spectroscopy. So this gives us great encouragement that we're doing something important and helpful and correct as part of a wider study on SS433 and friends. So this was published a few years ago with my colleagues Robert Lang, Steve Lee, and Anita Richards. So I hope I've given you a brief tour into the Global Jet Watch, which is the network of telescopes inspired by the microquasar SS433, but we now observe all sorts of other interesting time variable objects in the night sky, preferably those that are explosive. We love looking at novae. We love looking at Eta Carina. It's a particular favorite, as well as SS433 and other friends like that. If you'd like to know a little more about the Global Jet Watch, this is the website, and the bottom web link will take you to a 3-minute movie, which takes you inside one of our observatories. But with that, I will stop there and hand back to Francois.
Wow, Thank you for this wonderful and very, very impressive presentation. I loved it. Wow. We have I don't know if you can see the different comments that we have here and the questions.
I can't while I'm in screen share, but if I come out of screen share, I think that will happen. And yes, I can now see them.
Okay, so we have a few very interesting questions. Well, first, there is a remark in the chat from Patrick in Mexico saying that, well, Katherine, your outreach initiative in India is breathtaking. I hope someday we can connect Mexico into this global initiative. So
what a wonderful idea. What a wonderful idea.
The perfect and Drew also say that for SS43, my favorite space subject, Drew did present his talk yesterday, and so he knows what he's talking about. So that's very good also. Now I'm coming to the questions. There were at the beginning of the presentation a question from Patrick. Is this not a contradiction? The plasma is keeping away from a black hole when we are told that black holes work like vacuum cleaners, that is sucking in everything in its vicinity. The vicinity.
That's a very good question. Thank you, Patrick. So the important thing to realize is the little business about black holes sucking in everything is only true if you are closer to the black hole than the radius, which defines a mathematical surface known as the event horizon. Closer than that, you're absolutely right, everything gets sucked in. But the accretion disk that we're talking about, which is when matter sort of spirals in and slurps in, and we can see the spectral signature of that as well, that's considerably outside of the event horizon. So what you say about black holes sucking in everything is true if you're sufficiently close. You don't want to get sufficiently close, by the way. But if you take a broader picture, then it is not true that black holes suck in everything. On the contrary, black holes are very messy eaters. And in terms of collectively what comes towards them, they actually only swallow about 10%. Depends a little bit on the geometry, but about 10% of the matter that starts ambling towards them and getting closer and closer.
Oh. Wow. The next question, also from Patrick, were the result discovered thanks only to the high resolution spectroscopy or parallel observation in photometry? And by the way, I will add the question, what about the resolution you used for your observations?
Certainly. Well, just to answer the very bit first about spectroscopy versus photometry, photometry has historically played a very important part in studies of this object, because photometry gives us the whole picture, but at really very, very low indeed spectral resolution. But that's not to say that it's unimportant. So something I didn't get time to go into is the fact that there are a great many periodicities going on in this particular black hole binary, this particular microquasar. I mentioned to you the periodicity for the changing axes of the jet ejector. That's just under 6 months. The orbital period of the black hole orbiting around the normal star, that's about 13 days. There are some periodicities that are shorter still. There's one at 6.3 days, there's one at 5.8 days, and those involve, I don't know if you can see, I'm just looking for a pen. Here we go, I found a pen. This pen is here by the axis about which those jet axes precess. You don't just have precession in this object, you have nutation, which is to say that you have extra periodicities superimposed on the precession. Then you have longer precession timescales still. There's one on 550 days. So studies of time variable objects in the galaxy are not just for those of short attention spans. And that's what, and photometry has historically played an extremely important role in characterizing and measuring and flagging up these periodicities. Spectroscopy can then elucidate some of the underlying physics that photometry flags up. Sometimes, and I alluded to this briefly, it's very important indeed to know exactly how bright your emission lines are, and that's called spectrophotometry. And that's something that we're seeking to do with that pair of auxiliary cameras that are rigidly bolted underneath our telescopes. But Francois, I think you asked about the resolution of our spectroscopy. So the resolution of our spectrographs that are in the shiny red boxes, these are the ones designed by Steve Lee, the Aquila spectrographs. Their resolution is has an R, capital R, of about 4,000. But we've recently, as you know, taken delivery of one of your excellent L high-res spectrographs, which we love to use for just getting vastly higher sort of capital R values of about 20,000, just to help confirm that the Gaussian fitting that we think we're doing to deconstruct a particular stationary H-alpha complex or a red-shifted jet complex or a blue-shifted jet complex is indeed correct. So having the combination is really, really helpful. So I would say all of these things can play an important role in helping us characterize the object, because one thing I've learned in now quite a few years of studying this object is you think you understand it and it brings something out new from up its sleeve, and you just need to keep studying it with every telescopic means in your arsenal.
Well, there are still a few questions, but I think that we if we want to keep on time, maybe we have to stop here. And maybe you can answer some question with the Q&A tool. I cannot resist to a personal comment. We are here in the AAVSO workshop, and the AAVSO is an incredible organization that collects for decades and decades incredible data in photometry. And today, AAVSO is doing a lot of efforts to add the spectroscopy to the photometry. And when we listen to you, we say, wow, what the universe in front of us, and well, I want to be tomorrow. I cannot how to say that. This is something very, very important and very promising. And well, maybe Stella, you will add a comment on that, but how it is important that we also do spectroscopy with the AAVSO. That's wonderful.
We live in a wonderful universe, and it is elucidated by spectroscopy, and quite a lot of my research in recent years has been elucidated by the AAVSO. God bless the AAVSO, I say, and so grateful to everyone who contributes data for that. It's such a help. Thank you.
Okay, so I think that we could continue for hours. Thank you, Katherine. Thank you very much. Ken, maybe you can take the mic.
Sure. I'll take over and introduce the next speaker. But before I do, I just want to say, Katherine, that I echo Francois' comments. Wow. Thank you very much. We really appreciate your participation today, and I'm sure everybody just got a lot out of this presentation. It was excellent. So thank you very much. Next up, we have David Whelan, who's a professor at Austin College in Sherman, Texas. And I have to confess, this presentation that David is going to do has been something that I've been begging him for 3 years. And so I'm very excited to hear his presentation on using Python for data reduction. And David is an excellent speaker. I think everybody's going to really enjoy this. So with that, David, if you want to turn on your video and turn on your mic, and I will keep an eye on the questions for you. We'll do kind of the same thing as Katherine. We'll ask questions when we get to them at the end. So with that, David?
Thank you, Ken. My first question is, can you hear me?
And the answer is yes, and we can also see you.
Wonderful. Well, hello, everyone. Among both the panelists and the attendees, I saw a number of familiar faces, and it's really great to see you all here today. It's too bad that this year we had to do the spectroscopy workshop remotely, but I think the other side of that coin is that it has enabled more people from more places to join us, and I think that's really exciting as well. Thank you to Katherine for opening the day with such an inspiring talk. At the last two spectroscopy workshops, the Sacramento Mountain spectroscopy workshops, people may remember that I've spoken specifically about stellar spectroscopy, talking about how to understand what the spectrum is telling us physically about a star. But this year, Ken specifically asked me, as he already said, to delve a little deeper into the technical side of things. And so we are going in a different direction now. And I am fully aware that not all people are going to have a great deal of interest in this. And so this talk is really meant to support those kinds of people who do their data reduction, but don't really know what's going on behind the scenes. Maybe they have a package that they're using like ISIS from Shellyak or something else, but they've always wanted to try to learn more about the process. What I'm going to try to do is show you, by means of coding in front of you, what it looks like to reduce a very simple data set and do everything that's necessary in order to extract the spectrum and then calibrate it with wavelength. This is an enormous topic, obviously. It's something that requires years, really, in order to master in a big way. And so I'm naturally limited by the amount of time we have and understanding that not everybody is going to be really super interested in the nitty-gritty details. And so I'm doing the simplest spectral extraction that I could think of. And what that means is I'm not propagating my uncertainties. I'm not going to show you how to do that. I'm also not sharing with you any of my own routines that I've written, and I'm doing that on purpose. I have in the past lended or lent some of my my programs to other people, and it always just generates more questions. How does this work? Or why isn't this working on my machine? And this is not the time to help you with those kinds of questions, nor am I really the best person to do so on whatever your operating system platform is. So I have to limit myself to what I think is actually going to be understood and what you'll be able to walk away from this with. The very first thing I want to start with, therefore, is, if you'll look in the chat window, I'm about to write you my email address. Why am I writing you my email address? The reason I am writing you my email address is because if you find yourself interested or know that you are already interested in programming with Python and want to use what I write today as a template to launch yourself off into this world of programming, your data reduction, then I will share with you a OneDrive folder where you can access the data set that I'm talking about today and the small script that I write in order to try it on your own. Little heads up though, Python is a language that oftentimes I suggest that my students learn on their own or from a class. There are a lot of details, and I cannot possibly tell you the meaning of all of the things that I'm going to be talking about today. For instance, if you don't know what a module is, or if you don't know what it means to import a module, I'm not going to answer those kinds of questions today, and that's really just to save time. Those are the kinds of things that you can learn on your own if you're really interested in doing this. So again, by the time we're done, if you'd like to send me an email with your interest in the script that I write today, then I will share it with you. A little bit about me. I am a stellar spectroscopist. I am at Austin College, which is in the city of Sherman, Texas. We have a 24-inch telescope. It's built right on top of the Idea Center, which is our science building. And I use it as my primary tool for my research, which is spectral classification of B and A type stars. There are some people here who work with me closely, such as Drew and Ken and Joe Daglin, who I think I saw in the list of attendees. And we've been working closely on a number of small projects over time. One is about to be published, which is really exciting. And so the spectra that I'm using are relatively low resolution because we have to do spectral classification with them. Luckily, we have a perfect spectroscopic tool to do so, which is the L-Hi-Res 3, the same one that Katherine mentioned using. We use it too, and we love it. It is a great spectrograph, and we have a finger-length instrumentation microline camera attached to the back of it. It uses an E2V chip with 15 micron pixels. It's been coated so that it's sensitive in the ultraviolet and blue, which is of course where you need it in order to do spectral classification. By the time we're done today, you will actually see one of my spectra. And of course, if you want to see the OneDrive folder, you will also be able to access that spectrum for yourself. Now, data reduction. I know that some people here are very aware of all of the steps needed to do basic data reduction. They know what a flat field frame is. They know what dark current is, at least in principle, or at least as you see it on the image. They know what a bias voltage is and why you have to subtract it away from your image. For those who don't know it or who want to learn more, there is one single text that I recommend to everyone. It has been the most important for me in my career as a data reduction expert, I suppose. I think most people in astronomy are aware of it. It is Steve Howell's Handbook of CCD Astronomy. It's part of a series of books on observing from Cambridge University Press. It is a phenomenal little book, and I really do mean little. It's not very big, but it gives you everything that you need to know in order to understand the statistics and the data reduction techniques for working with charge-coupled device data. So if there's one book that I can recommend moving forward for people who are interested in using Python, it is this book to start. And there are, of course, other books as well. Francois obviously made a book that is, I think, probably going to increase in popularity in the coming years. So keep your eyes peeled for that one as well. So I think without further ado, why don't we get started? What I'm going to do is I'm going to share with you a text editor. And what you're going to see is just a white screen come up here. And the reason I'm showing you this text editor is because, of course, we're programming, aren't we? And so the very first thing that we want to do is begin to plan out our observations or our data reduction. So how are we going to do that? Well, I've called this this text document data-redux.py. .py is the typical suffix for Python routines, and of course it's labeled data redux because we want to do data reduction with it. I will be, I should probably put some kind of header on it, so a script for learning to use Python for reducing spectroscopic data. The data we will be using was taken at the Adams Observatory at Austin College on the 7th of October of this year. And it was one of my many observing sessions with students this semester. We had a good beginning of October, nice and clear. It's been pretty cloudy ever since, so I haven't observed too much since that date. I think the most recent date I've observed was the 13th of October. And now we want to go through the steps. What are the things that we do when we are reducing and extracting data in Python? Well, the single most important thing that we do when we are looking at data, or when we are reducing data, is to look at the data. So we are going to inspect the data using something like DS9. I prefer DS9 for doing data checks in order to look at them closely, and I will demonstrate its use here today. We always want to make sure that there are no problems with any of the frames. I'm sure you all do this anyway, and so I'm probably beating a dead horse, but it's always good to remind you that the fundamentals are absolutely essential. If you try to do, for instance, averages with frames that are not good quality, you're going to get not good quality results, and you might not know it. So always inspect your data. We'll do so with DS9. If you're not familiar with DS9, it is a FITS image viewer. You can also make 3-color images with it, and it's available from the Smithsonian. And of course, we're programming. So the next thing that we're going to do is to import the necessary modules for data reduction. And like I said, I don't want to supply you with any codes that you might not be able to get on your own, because otherwise you won't be able to launch into your career as a Python data reduction expert yourself. And so I'm only going to require modules that you can easily access for yourself. They include such things as SciPy, NumPy, Matplotlib. So if you're already familiar with Python, you'll probably know those names. If you are new to Python, these are the kinds of things that are easy to find and free as soon as you get them. Once we import our modules, we're going to set some variable names. So the kinds of variables that we're going to have to set are, for instance, the data directory path, the names of the files that we're going to need. I'm going to get the names of those files from my trusty observing log. I'm sure you all are very good observational astronomers, and you always log your results with very clear indications of what you've completed and what you've done and when. I always prefer to do so in paper, as you see, because online things can be corrupted, and the worst thing that could happen to this piece of paper is the whole building burns down, and then I think I've got bigger things to worry about, so I feel most comfortable using paper. So I'll use that to set my variable names. And once I've done that, we will start to read in the data. So step 4 in this process will be to actually start to read in that data that we've already inspected so that we can begin to manipulate it. Okay, so then begins the process of data reduction. And I'm going to use the standard procedures that you'll find pretty much anywhere. And so I'm actually going to begin to subdivide this. So the first thing that I want to do is I want to compute the bias level. And as you know, there are 2 other typical frames that are used for standard data reduction procedures, and that is the dark current and the flat field. And so we also want to create a median dark image. And a flat field. The LHIRAS-3 has an integrated flat field lamp, and so that's what I use to create my flat fields. Once I have all of the basic frames in place, I'm then going to actually do the data reduction, and so reduce the science image. And the way we do that is by taking the image of interest. We're going to be looking at an image of a spectrum of the star HD 886. HD 886 is a B24 spectroscopic standard. And so it has relatively strong hydrogen lines, but much stronger helium lines compared to hydrogen. And I think it's a really cool looking spectrum, so I think you'll enjoy it. we take that raw image and we're going to subtract away the dark image. And then we're going to divide by the flat field with the bias subtracted away from it. The dark image has the bias value in it, and so you don't want to make the mistake of double subtracting. If I'm subtracting away the dark image, then I am also subtracting away the bias value. So we'll do that. And then what follows next? An important step, I'm going to modify the header of the image to let us know that we have done the data reduction. And then we will want to do the spectral extraction. Now, the spectral extraction is the process by which we take the values that are on the image in units of analog to digital units, and we begin to count them up. One of the things I am not going to be doing today is calculating the gain and the read noise, which would enable us to convert the analog to digital units to units of number of electrons, which is much closer to the intensity of light that could be computed with the spectrum. Instead, we'll just keep it in units of analog to digital units throughout. That's again to save us on time. But the first step in extracting the spectrum is to find the spectrum. So we have to find the spectral trace. That is, you can't just, like your eye, know exactly where the spectrum is. You have to tell the computer where your spectrum is and between what bounds you want to count up values in order to be counted in the spectrum. So we have to find where that spectrum is. Once we've found where the spectrum is, we are going to do the actual extraction, which will be a simple addition in every single wavelength element across the array. And then we will begin to plot our results after we once again modify the header with the extraction parameters. That is the width of our, the center, the position of our spectrum, and the width of our spectral extraction window. After we've done that, we're going to do a spectral check, make sure that everything looks okay. And then the very last step will be to perform a wavelength calibration, where we will actually go through the steps of determining, based on the positions of known lines in the spectrum, what are the corresponding pixel values, and then fit a function to that, the correlation between the two in order to find the wavelength dispersion throughout the entire spectrum. And then we will plot the final spectrum, and then last of all, we will save our spectrum to a FITS file. So in mapping out our code, you can see that it really takes 8 distinct points. It takes quite a bit of time in order to do this properly. And there's quite a few details that go on behind the scenes in your data reduction software. You probably were aware of that, but it's interesting to see it all mapped out. And so why don't we begin by actually taking a look at the data. So I'm going to modify my share now so that I can show you my entire screen. That way we can flip between this window and the terminal window that I'm using here. Oh, wrong terminal window, sorry. Okay, so let's go to the data directory and start looking at some of the data. We're going to look at the data from the 7th, and so I'm going to that directory now. And what you can see is that I have a number of files from A0001 to 54 which are the first 54 images that I took at the observatory on the night of the 7th of October. And I've also got 25 dark field frames that I'm going to use to do a median combine. These 54 images include our science targets for the night, as well as our other calibration frames, the neon argon lamp that we can use for wavelength calibration, the bias images, and the flat field images. I'm going to take a close look at our science image first. I happen to know that that is AO-003.fit. I'm using DS9 to look at it, and so we begin DS9 here, and it will open up a new window, which will hopefully come to the front. There it is. I'm going to maximize this to the size of the window, and then I'm going to fit the spectral, the entire image into the screen so that you can see it there. And this is the spectrum that we took on the night of the 7th of HD 886. It is a beautiful spectrum going from the ultraviolet way over here on the right-hand side to the blue all the way over here on the left-hand side. You can see a couple of the absorption features in the spectrum. One of the absorption features right here is fairly prominent, and that is the H beta line in the spectrum. We have some helium lines that are prominent, for instance, here at 4922, here 4471. Here's the H gamma line in the hydrogen series, H delta, H epsilon, and H8. And so you can see that if you know the wavelengths of these things, we've got a spectral range here of about 3,850 angstroms out to a little past 4,950, about 4,970 or so. With our telescope here at Austin College, we have a dispersion with the L high res and with our camera of about 0.54 angstroms per pixel, which with a 32 micron slit, and that's about 2.7 pixels, gives us a spectral resolution of anywhere between about 2,700 and 3,500 across the spectral range. And so what we hope to do now is to take this spectrum out of the image in order to produce a one-dimensional spectrum of intensity as a function of wavelength. You can see that up in the upper left-hand corner here, the value that is shown on the image is being broadcast. And you can also see that the pixel values are being shown. I think my video has cut out. Can somebody confirm that for me?
Well, we can see your screen. We see the DS9 screen. No problem.
Okay, thank you. Okay, so this is one of our images. I'm going to open a second image of a flat field so that we can get a look at what a flat field looks like. And there's a specific reason why I want to show that to you. It's always good to know your data. And here is a flat field image taken with the internal flat field lamp of the L high res. You can see that there's a couple of spots on my CCD camera. It turns out that last winter we had a break in a gasket and ice crystals formed on the surface of the CCD. Of course, we sent it off immediately to get repaired, but there are some splotches on the CCD as a result. There's an old trace here from some residual bulk imaging. But the thing that I really want to show you is that if you look really closely right at the top of the image where my mouse is now, there appear to be a couple of rows that are discolored. They don't appear to be in keeping with the rest of the image here. And I'm going to zoom in on those just a little bit so that we can get a closer look. And now you can see actually really clearly that it's the last, it looks like 1, 2, 3 rows on the image, which are a little bit different from everything else. These are the overscan region on the CCD. And so they're typically not actually exposed, but when I had the flat field lamp on, they became saturated. And so when we are normalizing our flat field screen, we're going to have to watch out in order to make sure that we are not including those rows in our flat field normalization. The overscan region is useful in a number of ways. We can use it, for instance, to determine the bias value or the dark current in an image, but we won't be using them in that way today. I have separate bias frames, which I'm sure is the way that most people do things in order to demonstrate how we do a bias subtraction. So I'm going to close DS9 now, since you've had a chance now to see the couple of details about the image that I thought were really important for you to see. I've, of course, already done the checks for all of these data, so none of this is a surprise to me. Okay, now for importing the necessary modules. What I'm going to do now is actually cut and paste from, I've obviously already written this before because I wanted to make sure that I wouldn't make any mistakes. And so what I'm going to do is I'm going to cut and paste the actual code from another document. I'm going to bring it back here. And when I put it up there, I'm going to go through line by line so that you see what I've done. So the modules that I have to import, they're going to be several. I am using a program called PyFits. Now, PyFits is actually deprecated, and when I next upgrade my operating system, I think I'm going to transition to what's called AstroPy, which has its own input-output functions, including for FITS files, and so I will make that update. But you could use AstroPy already if you are just getting started. The other functions that I'm going to use are NumPy, SciPy, and I'm going to use the stats module. I'm going to use the median filter, and I'm going to use CurveFit, and I'm going to use the CurveFit in order to do our wavelength calibration. I'm also going to import a program that we are going to write. It's called Quad, and the Quad is actually just a really simple program. Let me bring it up for you here. It is a quadratic formula. Why am I importing a quadratic formula? You would like optimally for the wavelength calibration to be a linear wavelength calibration, meaning the dispersion is linear with wavelength. I have learned that that is mostly true when I am doing the broad spectra that I use for spectral classification, but due to some aberration, it's actually not quite linear. It's actually fit by a quadratic. Now, the x squared term is actually very small most of the time, and so it's actually quite a small change to the spectrum. If you are doing reduction at high resolution with L-high-res or a similar spectrograph, you probably will not need a quadratic formula. You will probably just need a linear function in order to do your wavelength calibration. So I'm going to copy over the quadratic formula to our folder so that we have that. I'm also importing the matplotlib routine. And matplotlib is a wonderful bunch of routines for plotting your spectra, plotting anything really. It's a very powerful tool, and I'll be using that to show things along the way. So once we've imported the necessary modules, it'll be time to set the variables, and the variables that I'm going to set, as I've already said, are things like the data directory path and the image paths for all of the images that we require. So for instance, here I have names for data dir. That would be our data directory, and I have it here set to the path to my data directory. I've also defined the images that we're going to be using. The image for HD886 itself is A0003 within this data directory. The neon argon lamp is image 18. The flat field images are 19 to 29, bias images 30 to 54. and the dark images were so labeled in the directory path. So once I have set all of those variable names, it's time to read in the data. And I want to first show you how to read in data using PyFits. It's actually very similar with AstroPy. You read in the HDU list using the open function, and then you can pull the data straight from that HDU list. It's also important to always pull the header so that you can modify it later so that it's clear what it is that you've done. And just to be clean with your data, I always like to close the HDU list afterwards. It saves RAM. And if you're opening a large number of images, or you're using a slightly older computer, such as I am today, it's always good to be a little nice to your memory. So we're going to have to do this not only for the image of our source, but we're going to have to do this for our neon argon lamp. And so I can cut and paste that up here now. I'm also going to have to do that for the flat field images, and you can see now that I've got a bit more code in order to read in all of the flat field images. So the first thing that I've done is I have opened the first image in the list of flat field images, and I've pulled out the data, and I have defined the size of the images in X and Y. So it's 2048 pixels by 515 pixels, including the overscan region. And then I make an array using NumPy that'll be the size of the image, and in the third dimension, however many images I've got. And so you end up with a three-dimensional image of all of your flat fields. And then I use a for loop here in order to open them all individually and stick them inside of that array. I'm going to do exactly the same thing for the biases and for the darks. Easy peasy, right? Especially when someone's doing the work for you. And so then we've read in all of our data. There it is. So now we get onto the actual fun stuff, the actual data reduction. And computing the median bias level is actually fairly straightforward. We can just use the median function in NumPy to do so. And it'll spit out a number to us. What is the median value of the bias for all of our bias images? You'll see that I'm using the entirety of the bias array. So all 25 bias images that I took for good statistics. I could probably do it safely with just one single image, but it's, redundancy is a good thing in science. So I've determined the median bias value for all of our images that we'll be able to subtract away. I'm going to do the same thing with the dark images, except you'll remember that there are some weirdnesses on my particular CCD. And even if there weren't those weirdnesses, and you probably have experienced this too, there are some pixels that for whatever reason are hotter. And I say hotter, meaning they let off more electrons per unit time without any light than the other pixels. And it could be because the substrate is thicker. It could be because it's being misread somehow, or any other number of little electronical reasons why that might be. And so I actually like to make a dark image, a full dark image, where the median dark image is computed on a pixel by pixel basis. So that way I'm not subtracting away a single median dark current value from all of my pixels, but I've specialized it to every single pixel. And I have found that this takes care of a number of the hot pixels across the entire array and avoids a lot of spikes in my spectrum when I'm finally looking at the final spectrum. In order to do this, of course, you have to have a high enough number of median images in order to have a statistically large sample. And so because I'm doing a median, I also have an odd number. I typically like to do anywhere between 15 and 25 median images in order to combine them for this process. Flat field imaging. Flat fields, I think they're the bane of everybody's existence, frankly. But we do the best we can. And what I've got here is the median flat field image. And so I take all the flat field images and I combine them just like I did with the dark. But the other thing that I want to do is I want to normalize it. I don't want to divide my entire spectrum by an enormous number, which was required in order to have good statistics on the flat field image. And so what I'm going to do is I'm going to normalize my flat field by first subtracting away the bias value and then dividing by the mode of the flat field image. The mode, as you remember, is the statistically most likely number. It's going to be probably slightly higher than the bias value itself, because of course it includes the dark current, although this was only a 30-second observation. And so actually the dark current is practically non-existent, I would be willing to bet. But you remember that overscan region that I mentioned before, those last 3 rows at the top of the image. And you remember that the first 2 of them were saturated. Well, yesterday when I was testing this script, I just determined that if I included those overscan rows in my mode calculation, then it gave me back a value of the saturated pixel, 65,535, because you had 2 full rows that all had exactly the same number on them. And so I had to exclude those rows when determining the mode. And so I only defined it between 0 and 511, the first 512 rows of the image. That way it's just the image portion, it's not the overscan region when computing the mode. And that gave me a mode that was much more realistic. And by the time I subtracted away the bias and divided by the mode value, it gave me a normalized flat field that looked better. And so that's what I've done here. Always know your overscan region. I guess that's the moral of 5.c. All right, once we've done that, we get to do the really actually fun thing, which is to reduce the image itself. And the final image is just going to be the original image minus the dark image divided by the normalized flat field. In the step previous, I removed the bias value, as you well know. And a question that sometimes comes up when I'm teaching my students about data reduction techniques is, well, don't you also have to subtract the bias value from the image? And of course, those students are always correct. That is absolutely what you have to do. But the wonderful thing about subtracting an entire image away from the raw image is that you are subtracting all the entire value of that dark image away, not just the dark current, but also the bias, which of course is in every single image. And so we've made ourselves made our lives a little bit easier by choosing to do just a median combine of the images above. Then we have to do our necessary stuff of appending some verbal stuff to the header. I've kept it simple. All I've done is I've said that we're going to add a new header keyword called reduced, and I've given the formula for our data reduction procedure in the header, so that if anybody had any questions about how we've done it, now they know. All right, now that we have a final image that we can finally take a spectrum of, we now have to do the spectral extraction. I am going to show you some stuff really quickly because I'm starting to run out of time. The first thing that we want to do is show the trace. And so I show the trace here, which is essentially flattening it in the X direction so that we just see the dispersion of the profile. And so I'm going to plot that for you so that you get to see that. But then the next thing we want to do is actually find where is the peak in that dispersion profile. And so we find the peak. Oh, I should probably actually put a comment in there because people are going to want to know where that is. Once I've found the position where the peak is, that's of course where the spectrum is going to be, I'm going to just magically make up a number for what I think is the width of our dispersion. Normally what I do is I fit a Gaussian to the dispersion profile, and I find the standard deviation of that Gaussian, and that's my, I use that to find the full width at half maximum for my dispersion profile, and I use that as my extraction window. I'm not going to go through all of those steps because there's a lot of nitty-gritty stuff that could just confuse you later. And so that's the kind of thing that once you've become familiar with these early steps, you'll be able to do a little better later. Then I'm going to plot the trace with that window around it. And I'm going to define the values of my extraction window. And then after we've done all of that, we are actually going to do the extraction. And so I begin that by defining a new array. I'm calling it SP for spectrum, and element by element, we will just total up between the high and the low values in our dispersion profile that looks like it's good. Then we will once again append some keywords to the header in order to tell whoever comes after us what it is that we have done. We will, of course, take a look at our spectrum to make sure it looks pretty. And then we will go on to wavelength calibration. Wavelength calibration is probably the most difficult for people to understand how to do. I'm going to show you what a lamp spectrum looks like, and I'm going to compare it to the spectrum that we've already got. And so that way we can see the correspondence between the lines on the lamp spectrum and the lines, the absorption lines in the stellar spectrum that we have. I've already found the X value and calibrated line spectrum values for the lamp. And so I will just simply put those in here, and then we will use curve fit in order to fit a function between our X valued pixels, the number of pixels in the spectrum, and the wavelengths that we have chosen. And we will then use that to make a new array of wavelength values, WVARR, wave array, wavelength array. Once we've done that, we'll do the fun thing, which is actually plotting the final spectrum. So we'll be able to see how it looks with wavelengths on the x-axis. And then last but not least, we will, of course, save our spectrum as a FITS file. Always important to record your results. Okay, that's it. Only 180 lines of code. Really, that's not so bad. And if anybody is used to programming with some of the more difficult to program in languages, such as Fortran or C or Perl, then you know that that actually is really not all that bad at all. And that's why I think Ken was interested in me talking about Python, because if there's any computer language that looks more like actually written English, this would be it. So, are you ready? Shall we do it? What I'm going to do is, no, wrong one. I did it again. I am now going to go to my data reduction folder, ASW 2020, here we are. You'll see that I have the quad.py, the quadratic formula that I mentioned earlier already in there. We've also got our data redux.py that we've just been editing all in there. And so I should be able to cut line by line all of the pieces. And I'm not going to do a full script, just like, plug it in, boom, go, and let all the things follow. I'm going to do it step by step so that you see every step. So the first step, of course, is to start Python. I realize that this will look different probably from what you are going to use because I am using Linux. You are probably going to be using Windows or Mac. And so how you interface with the Python command line will probably look different. But the first thing we do is we copy all of our commands for importing our modules. And so now the computer has all of that information at its disposal. Then we define all of our variables. Yay, that was easy. And we start to read in the data. Okay. I just did it. I just read in our first image. And so I want to take a look, hd886._d for data. Everybody has their own methods for naming variables. Mine are probably just as dim-witted as anybody else's. But if we take a look in Python at what it'll give us, it just gives us a whole bunch of values. In fact, that's not too useful. If you use the .shape command, we can actually determine the size of our array. And we already knew this. It was 515 by 2048. But that's just a good confirmation that all is looking good. We know that it's an array. We know that this data type is 16-bit integer because it says so right over here. And so everything is looking hunky-dory.
David?
All right, so I'm going to read in now the neon argon lamp image. Done. Now I'm going to read in all of the flat field images. So let's do that. Okay, that was easy. And if we take a look at our array of flat field images, we can see that it is a three-dimensional array. It's got the number of pixels in the X direction, the Y direction, and then stacked the number of total flat field images. And as you see, I have 11 because I choose to do median combinations, and so I like to have an odd number.
David.
Yes.
Ken here. We're running a little bit behind, but if you could maybe take another 5 minutes.
That's what I'm hoping to do.
Okay, sounds good. Thank you.
Yep. That's why I'm going quickly through these last steps. Read in the data, the rest of the data. Read in the, what was that? Biases, read in the darks, all set there. Okay, compute the bias level. Simple command, and if we look at the value there, we get a value of 959 analog to digital units, pretty straightforward. Compute the median dark image. Boom, easy. This step takes a little longer. Computing a statistical mode in Python always takes a little bit of time, so this command is going to lag for about 10 seconds, 10 valuable seconds. Oh gosh, I'm so over time. It's hard when you want to fit in so many talks in a day, isn't it? Come on, computer, you can do it. Anybody know any good jokes?
David, while that's running, I'll ask you one of the questions that we
Sure.
have. Is it easy to extend this code to stack several sub-exposures?
Oh, absolutely. Yes. I'm only doing one image today because I thought that was the easiest to start with, but routinely I make arrays of large numbers of images that I reduce simultaneously.
Great.
And you can essentially read them in the same way that I do the flat fields and the biases here. So it's a relatively easy thing to do. Okay, I'm going to reduce the image, modify the header. I'm going to create the trace. So this is our first plot. Ta-da! This, if you took a cross-section of our spectrum, is what it would look like. You have a peak where the spectrum is, and it's otherwise really close to zero. If I do a zoom in here, just really quickly, you can see that it very definitely peaks at one specific value. It looks like about 170 on the x-axis. And so that looks pretty darn good. What we want to do, though, is tell the computer that the center is there. And so we do a simple where command in order to find it. mx is my middle of the x dispersion. It has that pixel value of 170 that we were looking for. And as I said before, I have defined the regions around the spectrum as about 3 pixels. Normally, I would actually fit a Gaussian in order to determine this, but this is quick and dirty, and frankly, will get you a really good spectrum even without doing fancier work. And so if we take a zoom in, what I have here is the same dispersion I showed before with a line showing the center pixel and a green box showing the region of the spectrum that we are going to use to total up the values at every single wavelength element in order to find our spectrum. And so without further ado, guess what? I just extracted the spectrum. Gosh, it's such a letdown. It took no time at all with all that preparatory work. So let's take a look at it, see what it looks like. Hey, it's a spectrum. It's got lines on it. It's a star. Also, it's backwards. This is H beta over here. This is H gamma. This is H delta, H epsilon, H8. So we have decreasing wavelength to the right. You'll notice that that's exactly the way it was on the image itself. So that's no surprise. But of course, we have to make an adjustment for that. So if we take a quick look at our lamp spectrum and take a look at it. The first image that I have here is the lamp spectrum itself. So this is the integrated flat field lamp in the L high res 3. It uses neon and argon in the discharge tube, and so it's got a whole bunch of lines. If we overplot the spectrum of our star with the lines from the neon argon lamp, you can see that there's got to be some kind of correlation between the two. That's really the only point of this plot. What I did beforehand is a rough and dirty. Here are the pixel values that seem to match with wavelengths of known lines in the neon argon spectrum. And then I use curve-fit in order to determine our wavelength array. And so we can see that it's got values from about 3860 angstroms to 4980 or so. And so we can plot our spectrum as a function of wavelength now. And so that's what we've got here. This is the raw spectrum of HD 886 that was secured at the Adams Observatory here at Austin College as a function of wavelength. Ta-da. And of course, if you look really closely and you start comparing wavelengths, you'll see that it's actually off a little bit. Your homework assignment, if you were to have such a thing, would be to improve upon my estimates. All right, so finally I saved my spectrum, and that's it. La-di-da, we're done. And so I will take questions now, if there are any, in the last couple of minutes that Ken can afford me.
All right. Well, first of all, let me say, I think this was a great presentation. I think that everybody got a lot out of it. If you're interested in doing your own coding, this is a way that you can get started. And David has volunteered to share some of this material. He already put his email address out there for anybody who's interested, so that's great. If you're not looking to code in the future, then I think this is still really valuable because it gives you an idea what's involved in doing data reduction in software. So when you go on to the next breakout session for ISIS or Demetra or RSpec, it gives you a sense of what's involved behind the scenes to be able to take all of the raw data and do the data reduction and come up with the spectra. So it's in my mind, a very valuable learning experience. Now, Andy Howell was asking about getting a copy of the code. Is that what you can do if people send you an email, David?
Yes, Andy, Stephen, anybody else, those are the two names that I saw in the chat. Anybody who wants this code, send me an email and I will share with you a folder which has access to the data, to the code, and that way you can do exactly what I just did today.
Okay, great. And I'm assuming if people have a couple of follow-up questions, they could send that to you in email as well.
Sure, that would be fine.
Okay. All right. Well, with that, I think we need to move on to the breakout sessions. There was a break scheduled, but I would suggest that people, as quickly as possible, get over to the breakout sessions. If you're going to the Demetra session, you don't have to do anything at all. You're here. If you're going to ISIS or RSpec, Lindsay sent out a link to a website that has links in it for that. And I see that Lindsay's available here to give us any added direction that we might need because she's way better at this than I am. And then we have the breakout sessions followed by a break, and then Christian's UVEX data reduction and Steve Shore's conversation. So lots of stuff going on today, but I'll turn it over to Lindsay.
Hi everyone. Yes, if you didn't get your email or it's lost in the abyss of your email, what I emailed out is essentially right here. You all, if you haven't already, are going to go to www.aavso.org/links. Very simple URL, and there you will find the links and the password for the ISIS session and for the RSpec session. If you plan on attending the Demetra session by Francois, please stay here in the main webinar. You don't need to log out. You don't need to sign in anywhere. If you're going to ISIS, leave this webinar. The red leave button is in the bottom right corner of your screen. And then you're going to go to that link and click on the ISIS link. Same thing for RSpec. You're going to leave this webinar by clicking that red leave button, and then you're going to go here and click on the RSpec link, and just know that each of those links also has a password associated with it that you're going to type in just for security reasons. Once those end, those sessions will just be ended. So you'll be kicked out of them once they're over. And then you're going to log back into this webinar using the same confirmation registration email link that you did this morning to get here. If you have questions, feel free to email me, lward@aavso.org. And so, all right, I think that commences it. We can all just go into our breakout sessions. Everyone is waiting for you.
Thank you, Lindsay. Thank you, David. And I understand that there's been some issues, I guess, with my connection, with me breaking up some. I'll leave the video off for the moment. Maybe that will help some. It's kind of amazing that I still have an internet connection at all, given how windy it is here today. But I would like to turn things over to Francois to start in on Demetra.
Thank you, David. Okay, yes, and thank you, Ken. Sorry. And well, maybe we wait a few seconds until we have given some time to everybody to switch to the other meetings, or do you think that I can start right now? Well, maybe I can start.
You can go ahead and start, Francois.
Okay. Anyway, what I want to do here is to talk about Demetra. And by the way, well, I don't know if you're still online, David, but your talk was wonderful, and this is very, very interesting for me to see how you present things, and I love that. And what I will present with Demetra is something very different, because we are not under Linux, we are under Windows, and so we have a different approach because we want to make things very simple. But I'm totally in phase with all what you are doing, and I hope that one day we will connect Demetra to Python process in order to be able to really to make easier to control the process. And in fact, well, I know it is feasible because I have some experience in Python, but really what you showed is that it's really not complex to do. So thank you very much.
Very cool.
Anyway, I
Thanks,
switch to
Francois.
Demetra. And I switch to the Demetra, and well, I just want to have a quick introduction to what is Demetra, and at the end, the idea is to do the same. And I will do a live demonstration. I have only a few slides to show you, to show, and I will switch to a live demonstration of Demetra. It will be much better, and maybe you can have questions and so on. And as usual, Ken, you can interrupt me when you want. Okay. Well,
Yes,
I don't know if
I'll keep an eye on the questions. If there's something urgent, I'll ask you. Otherwise, okay, we can save the questions to the end, and we should be good to go.
Well, perfect. Thank you. You know that we want, well, I'm not the only one, but we want to make spectroscopy easier and easier to embed more and more people in the adventure. And we know that it is quite complex to do, and we can use the software to make things easier. And I like to say that a long time ago, well, several years ago, I did write a letter to Santa Claus. I don't know if it works in English, but in French we say j'ai écrit une lettre au Père Noël. And so I had a dream, and I just wanted to have a software that makes my life easier. And so to this software, I wanted to ask, well, please help me during my observation to get the best for my instrument. So this is something that several people already told, and I remember Woody yesterday saying, so the goal is really to get the best from the instrument. So during the night, during the observing session, please tell me what image do I cry, and by the way, some of you, well, David, it looks like you're observing very often, but so a lot of people are not observing very often, and when you observe, it's important to have the software to help you to remember exactly what it is to acquire. I want to ask this software also tell me if my images are correct or not, if there is a bug somewhere or not. So I need to have some tools, very easy to use tools to check that the images are correct. Help me to define the critical parameters, mainly for the data reduction or all the parameters you need to process the data. Please process all the data in a fast and easy way, because well, we have seen that the data reduction process is a well, even if David showed that in few lines, this is anyway a quite complex process, and we'd like to have something very very fast and easy. Okay, and by the way, allow me to describe the observation I'm currently doing, and especially I'm talking about the logbook. Again, David, you mentioned that this is very important during the observing session, that you show you write everything what happens to keep it in memory. And there is something important also, that when I go to bed, I need that the data are fully processed. This is something important because we know as amateurs, a lot of people like to observe and say, well, I put the data on my disk, and tomorrow I will process my data. The point is that tomorrow is another day, and tomorrow we have a lot of things to do. And while it not be tomorrow, but it will be next weekend or next week, or and in fact, at the end, a lot of data are just dead in the hard disk and never processed. So I wanted to have something very quickly done, and to say, well, it is so easy to process the data that when I go to bed, it's done. Okay, I want to take care also, I want this software to take care of the data management and the again, you talked about that, the way, David, the way to archive or to organize the data and to archive them. So this is important, and we have to archive them to make things clear, to recover the data in few days, but also we have to recover the data in 10 or 20 years from now. So it's important to look at that. And by the way, so I want that you help me to do things very automatically, quickly, and easy, but I want to remain the boss, and I want always to be free to do what I want to do, and I want to keep the control of my data. So I don't want to have a black box in which I just click on a button, and at the end I don't know exactly what happened to my data. Okay, so this was my dream, in fact, and I think that with the time, I think that we did it, and well, this so this is the first the main page of Demetra when you open it, and this is just to show that today we have 3 available versions of Demetra, and the 4th one is to come soon, of course, for the UVEX. So the initial version was for the LP600, and we have added recently the LISA, and the eShell is almost done, which is much more complex than the LP and LISA data, but it is done, and we will make it available soon. And by the way, if you want to have it right now, we can give the link to you, because it is already available. And we have spent some time with a team of beta testers who did a wonderful job. Some of them are online right now, and so it's now ready. We just have to make it available, and it will be done soon. And of course, the UVEX, we talked about the UVEX yesterday, and we'll have a UVEX version of Demetra. Okay. Well, so that's it. Now I can switch. I will stop sharing this screen, and I will switch to my Windows page, if I can find it. Where is it? Here it is. Okay, so can you see my screen? If anybody
Yes,
can, yeah.
we can see it fine.
Okay, perfect. Okay, so see, this is the Demetra welcome page, and in fact, in Demetra we have mainly 2 modules. One is to manage the observations, and the other one is to take spectra. So this is the acquisition module. The most important is the one to manage the observations, and of course, this one will use the acquisition module. Okay, so I go to this management of observation tool. didn't work, does it? Interesting. Oh, here it is. Sorry, it was already open. In fact, sorry. So when I come here, so I go directly to the directory where I have put my observations. And by the way, well, so Demetra is free. Demetra is you can download it from our website. It runs only under Windows, but you can use it. And Demetra comes with some demonstration demo data. So this is the demo data that comes with Demetra. So you can really download the software and do exactly what I'm doing with you today. Okay. In this case, we have the idea is that we have an observing session, and observing session means one directory. Okay, so the directory is defined here. So this is the directory called the demo alp. Okay, and I can, of course, I can change this folder, which means that I will change the session, the observing session, and I can also explore this folder. Okay, so it's important to say that all the data of the sessions are put in a given folder. And this is exactly the same way as David did. We all have our own way to organize the data. In Demetra, this is something very simple. One observing session is one folder. Okay. In this folder, so we have the logbook here. So this is very important. So I can open it, or I can directly write here, but I can open it and I can even put some templates data. For instance, so if I want to write something saying, well, I've just added an observation, or we just had some clouds, or I don't know, whatever is important during the observation, I can also add the timing stamp here and say, well, at this moment we had clouds, for instance. So I can put anything I want here, and there is no need to save it because it is saved automatically. And by the way, I can also write it directly here. So this is exactly the same. This is just a question of being comfortable with the interface. Okay, so now I see that I have 4 observations here, and the first one is I will look at is the Vega one. And when I click on one of these observations, I will see the different tabs here. By the way, all these observations are green, so it means that they are completed. So it means that I can really go to bed. Okay, this is important. If I want to create a new observation, for instance, I can copy this one. I can right click and copy this observation and say, well, it will be a new observation. Well, the name is not important, and I can define to duplicate some of the files. I will go back in detail for that. In this case, if I create a new observation, it is red. It is red. It means that I have some data which are missing, and I can follow the colors here to see what happens. First, in the definition, I've not given the name of my target. I can say, well, my preferred star. I have a UK keyboard which will not work with me. Okay. Okay. And so as soon as I give a name to my to my observation, it becomes green. Okay, and I can look at the images and say, well, I have some offsets and so on, but I don't have any objects because I decided not to copy them from the previous observation. So in this case, the basket here is empty, and then it is in red. So the software draws my attention to what is missing to get a good observation. Okay, so now I just remove this observation that I just created. I come back to my Vega observation, and if I come to I have a first tab which is for the definition and the context of the observation. So who is the observer, where did observe, and with which instruments. I have some information on the target I observed. And the second tab is I have some baskets. And we have defined these baskets because we consider that if we want to have a good quality spectrum at the end of the day, we need to take the spectrum of the target, the object, of course. We have to take bias, okay? We have to take dark images, flat images, and calibration images, okay? And for each of them, I can double click on the image and see in the bottom of the screen the contents of the image. Okay, I can do that. I can enlarge it here with this small button, so it uses the full width of the image. Okay, and I can even show a quick profile here. Okay, so and this works even during the acquisition. Okay, so I have a small tool, and if I go, for instance, I just have to double click on one image and to see the next one, and you can see the change from one image to the other, and you can see it in the 2D image, and you can also see it in the profile. Okay, which is something very important. And as David, you mentioned, and again, I fully agree with that. You have to check your data, and this is a very simple way to check your data to go quickly from one image to the other to check that there is no big problem. And by the way, if there is a problem on this image, you just have to click on it. I think I can right click. Yes, I can remove it. Why I can't remove it directly, I don't know, but I can remove it by suppressing this image, and that's it. By the way, you can see that the image has numbers, which is quite usual, but the name has been created automatically by Demetra, okay, during the acquisition. And if you want, you can use your own image that you did take with your own acquisition system, if you prefer, and you can add the image using this button from your hard disk. But keep in mind that there is no naming condition. So Demetra gives a name, an automatic name with the name of the star, the date, the time, and an index. But there is no rule, so I can add a file which is A and another one which is W. Demetra doesn't care. This is just a list of images. Okay, so I can do that the same for the bias. Well, the offset is not the right name in English, but so this is the bias image. This is a flat image. And each time I can click on fit and auto here to see my fit image, and immediately I can see the fit profile at the same time. Okay, and I can also look at my calibration images and see the profile immediately. Okay, and again I can change the thresholds, and if I want to see all the lines, I can manually change the threshold, and then I can see all the details in my image. Okay, so once all the baskets here are filled, and then we have images in all the baskets, I can go to the next step. By the way, if I don't have any image here, I can either choose to add them from the hard disk if you have already made the image with your own installation, okay, your own system, or you can go to the acquiring module, acquisition module. You can click on acquire, and then you can connect to your camera. So in this case, I have no camera. Well, I have no camera connected. This is the ASCOM simulator. I don't know what happens exactly, but well, I can try and start. If I take one second image, well, okay, this is the demo image from the ASCOM driver. So I have no real camera connected, but the idea is here. I can select the number of exposure, the exposure time, of course, and I can select the binning, and I can have a preview just to make sure that I have the right information. I can, for instance, draw a rectangle here and right click and have the statistics in the image. So I know in this in this case that the maximum value is 300 ADUs. So I'm far from being saturated, of course. And by the way, I can also add a tool here, the stats tool here, that gives me the same result, and I can see in live the value of the maximum value and so on. So, and when I have a rectangle somewhere, the stats are linked to this rectangle. But if I double click and remove the rectangle, the data I have here are related to the whole image. Okay, yes, well, to the whole image. And when I'm okay with the exposure time and so on, I can just go to the acquire menu, and then I can, for instance, in this case, I say, okay, I will add 3 images of 1 second in my image basket. Okay, so here it is done. Again, these images are nothing, but they are stupid. But this is just to show the idea. I can go back to my observation here, and if I go to my object, I will see. I should see. Sorry, I was in the calibration box, so basket. So this is why the Vega images have been put in this basket. So it's my mistake. And anyway, I can look at the image, and I can again I can see the image and so on. So I can switch from the acquisition module to the data reduction module. Okay, and of course, because there are not calibration images, I remove these calibration here. Okay, so this is the idea. You can either take the image from your hard disk, or you can acquire the images, and then once you have acquired all the information, you can just go to the data reduction. By the way, there is something important here. You can see that if I go back to the Vega image, I can select. I can look at have some blue and yellow bands, and these blue and yellow bands are made to select where is exactly the spectrum. This is exactly the same operation as you did, David. And I can also select the position of the sky background that I will subtract. Oops, sorry, I made a mistake. This is this one, and this is this one. Okay, so I can change this, and I always have to make sure that even if I switch from one image to the other, the image is right in the blue part of the spectrum. Okay, because the spectrum area, the extraction of the spectrum will be made in the blue part of the screen. Okay, and now we just have to go to the data reduction screen, and remember that I did ask to Santa Claus to give me a software that allows me to do the data reduction in one click. So here's how it works. So this so it is in live. Again, as soon as the step is green, the result is okay. And then I have at the end the result of the operation. And by the way, we have automatically added in these results the Balmer lines just to make sure that the wavelength calibration was correct. Okay, so I'm happy because I did that in one click. But remember that I wanted to have also something on which I do have the control of what happens to my images. Okay, and for instance, well, you see that the process is really made in several steps. Well, by the way, I don't know where I am in the timing. Can you tell me if you quickly, do you have an idea, how long I do have to, I still have to finish?
Well, that's a good question, Francois. You probably, I mean, the original schedule was that you have until 40 after the hour, so you would have 30 more minutes if we stick with the original schedule.
Okay. So the 30. Okay.
But,
It will be enough.
maybe you go over a few minutes. It's not the end of the world. It's okay.
No, okay. I know. Thank you, Ken. So you can see that the data reduction process is some steps in the process, and again, this is very close to what David you showed with the Python, and this is why I have a dream, which is that one day we could connect these steps to Python script, in fact, to make it more flexible and more adaptable. But well, I still have a lot of dreams, so maybe we'll do it one day. By the way, each step, you can click on each step, and for each step you have some information there. And if I look at the masters, for instance, I can always double click on the image before the processing, and as always, I can fit an auto to have my image here and to see what is the result. And I can move across all the images. Okay, so these are the different offset bias images I do have. And I can also double click on the result of the operation. Okay, so we can see here that this is noisy. After we do the median image, then we have less noise in the image, and this is of course the goal. And you can do that for all. You can do that for all the images. You can do the same, and you can see the difference between and after each operation. One of the operations that I like is this. When I look at the calibration images, for instance, I can look and see if I extend the image, if I remove, change the threshold, so you can see the lines here. And if I look at the after the operation of geometrical corrections, then you see that all the lines are vertical. They are bending before, a little bit before, slanted and bended. And after that operation, they are perfectly straight and vertical. Okay, so you can do that for any operation. You can rerun any operation manually. You can do exactly what you want, in fact, and really you have the control on the operation, and of course at the end you have the result of your process, which is the totally response corrected spectrum and so on. Well, by the way, for the response step, I did apply a response curve. Of course, this is something important, of course, and this response curve has been done separately with this Vega spectrum. Okay, so we have a tool here to build the response curve of the instrument. I will not go too much in detail right now because it will take time, but we really have all what we need here. And well, this is the idea. You can really have the control of each step and see for, the extraction, for instance. Before the extraction, you have the 2D image, which is corrected from all the flat bias and so on. And you can see the result after the extraction, which is, of course, a 2D profile. And here, oops, there is a problem. So here is the extraction. Okay, if you look at the calibration step, you can see that you have at the beginning you have the spectrum from Vega in pixel units, okay, on the CCD, and after the calibration step, you have the same profile, but which has been resampled to have a linear scale, horizontal scale, and it has been wavelengths calibrated, and then we have been able to add a visual colored rule to give an idea of where we are in the spectrum. Okay, and well, you have seen almost all the things. You can we have a last output tab in which I can produce some data, and again I have a lot of possibilities to add, for instance, a 2D spectrum in my data or not. I can add axis in the graph or not. I can do whatever I want. In fact, I can change the dimensions and so on. And I can produce, of course, the system will produce a fit file, a totally normal fit file. But we can also export in PNG, SVG, and which is easy to when you want to add some details on your image. And you can also create a PDF file. And I can also add some lines. For instance, in this case, I can add all the Balmer lines here. I can add them, and then I refresh the drawing. It should work. Well, okay, I don't know what happens right now, but sure, of course I did remove that, and then I can show all the Balmer lines in my graph, and I can, of course, I can add the lines I want. I can show any line in my spectrum if I want to do that. Okay, and then if I create that, I will have a PNG document, and if I open this PNG document, I can see the result, and then I can send my what's that? I don't know. Well, this is some Windows things, and it should work, I think. Yes, so this is the result. This is the graph I've produced in PNG. So you can add that in a message, send it to your friends or your colleagues and so on. Okay, so this is again, this is the idea. I think that we have I have the software I dreamt about for Christmas, and really it does the job now. Just to show you, I want now to, well, by the way, no, before doing that, after I've done that, this is very easy to create a new observation. Again, I can just click on Vega, copy the image, okay, go to Deneb, for instance, sorry. Okay, and I will create a new observation. In this case, I just have to mention that this is Deneb observation. Go to the images, say, okay, I just have to acquire my data to get my, so I have to move the telescope towards Deneb and launch my acquisition images, go back to here, and I will see the images. And then, because all the parameters are exactly the same, in fact, I can go to the data reduction and run the data reduction immediately. Okay, so it's engraved for now, because I cannot do it because I don't have my images, the missing images, but I can do that. So if I take another star, I can really add my objects. I can, for instance, if I take this YCVN, which is a carbon star with a wonderful profile, I can see here, I can see the profile itself, and which is very complex. And then I just have to collect my data. And now I go to the data reduction, I click on that, and I do have the result. And I can even, well, the result is automatically saved in FIT and PNG and PDF if I want, and everything. So here is the result, and it is fully processed, calibrated, and so on. Okay, now I just want to switch to another version of Demetra, which is the eShell. And this is just to show you how it works. So the principle is the same. What's that? Okay, so I don't know what happens. I love that. Anyway, I'm now in the eShell version. And by the way, this is exactly the same the same Demetra. Okay, so we say that we have a Demetra version for the ELISA, for the LP600, for the eShell, and soon for the UVEX. But in fact, this is all the same. We just have to change the process here. So in this case, I am in the process version, in the eShell version, just by doing this. And now I can see on the first front page that we switch to the eShell process. Okay. The idea is exactly the same. Okay, I can switch, I can click on the Vega image. In this case, I do have all the information. The context is exactly the same. I do have, in fact, the same baskets, but the difference is that a Vega image in eShell spectroscopy is really very, very different. But the idea is the same. I can look at this this order. I can even change the order I'm looking at. You know, so this is the blue the blue screen here, which is moving. I'm not sure. Sorry. Okay, so I can change the profile I'm looking at. Okay, so I do have this visualization of all the orders, which is much more complex than what we have, of course, for the LP or the ELISA. Okay, and this is also the calibration image. So if I look at this calibration image, here is what you will see. So you will see all the thorium and argon emission lines. So this is a very complex image. But again, the idea is the same. And when I've made all my images, I can go to the data reduction and run. So you will see that the process is more complex. So there are much more steps for the process. And by the way, the time to run all the data is significantly longer. So I hope that there will be no problem here, but the idea is the same. You go the steps becoming green one after the other. And then you have a log file here that gives you all the elements on what happens about the processing. Okay, and so you see it's working, and it takes some time, of course. And by the way, the Zoom connection takes some CPU percentage, so it is a little bit longer, but again, it will be a few seconds to go up to the end of the system. And okay, so this is the calibration detection. So it will take 2 orders to tune the calibration parameters, and the calibration is now done. The response correction is done, and the final operation is very simple. There is just the last operation is just to create a merge spectrum, which is really a complementary operation. But here is the result. Okay, and this is amazing because this is a full spectrum from Vega. Okay, so the response curve correction is not that good, but this is really for technical reasons. It's not the idea. You can see all the different orders. Okay, and this is the merge spectrum, and of course this is the same. You can go to each step and run manually and check what is before and after each step at for each operation. You can control that, and you can also go to the output tab, and in this case you will see all the orders that are merged again in a single spectrum here. But here you can really you can zoom in any part of the spectrum, and you will have details and details and details. So this is what is totally crazy with the e-shell spectroscopy. Okay, so and then you have the details with the colors of all the orders here. Okay, so again, this is the how it works with the e-shell. So this is much more complex with the e-shell than with an LP or with a single order system. But well, I think Santa Claus did a good job, in fact, and this is already Christmas, in fact. Okay, so I stop sharing my screen and I come back to the other slides, the latest slides I have. So I was here, and just some to think about this. What is important in Demetra? I think that we in fact, when we work on that, when we started to develop this software, it was with a software developer whose name is Nicolas Durand. When we started, we didn't know exactly where we are going to. So we did want to have some goals, but we didn't know exactly how to do that. And now when we learned a lot by doing this, and today I think that we can make some go a step behind, saying, well, okay, so what is important here? So first, we have a single software for both acquisition and data reduction. Okay, so this is the first thing. It's important to have some help during the acquisition. Well, I didn't show you, but we have a system that detects if you have a saturation of your images in the blue part of the spectrum. So in the important part, in the blue part of the image, sorry, in the important part for the spectrum. And we can detect that. We can display in real time, even during the acquisition, the profile of your spectrum, which is very useful and important to check that everything is okay. We have in real time all the important information, that the number of ADUs and so on, so you can really control everything. Something which is important is the observing session management. One observing session is one directory. That's it. There is no negotiation. If you have to take some images from another directory on your disk because you have your own system to manage your data, which is your right, of course. In this case, Demetra will copy this data in the session directory. In this way, you can save, you can archive. We have even some archiving tool that I didn't show you. But you can archive the data and keep the data safe, and you are sure that if you come back to this directory in 10 years from now, you can just rerun the data and it will work the same. Okay, so this is something very important, and to make things simple. So if you want that thing works, they must be simple. The second point that we have understood is that the data reduction process is the core. Okay, so we have I've told you that we have a version of Demetra for ALPI, for the UVEX, for DHL, and so on. In fact, the differences are not that big, but what is important is when you take your data, it is very important to know which data you have to take to make sure that the data reduction will be easy. Okay, so if we can do it in one click, this is not because there is a magic, or it's not because we are better than the others. This is just that we organize the data at the beginning, and we make sure that the data we collect are easy to process, and then we can make the data reduction automatic. Okay, so this is what makes things working. And then the data reduction process is the core, and in fact, this is, you just have to think that during the observation, you only have to collect the data that will fit in the data reduction process. Okay, so the data reduction process is even more important than the acquisition step. Yeah, in fact, when you acquire your images, you are acquiring data that you will put in the data reduction process. Something also very important, and that I think that we have to make it a general rule, an observation is a set of images. Okay, so you have to make sure that you keep together the target image, the flat image, the calibration images, and so on, to make sure that it makes a consistent set of images. You know, you've seen that in Demetra, we don't really take care about the image naming, and you don't have to remember that this flat was made after this target and so on. All is in the observation management, and this is kept in memory by Demetra. And by the way, we have a text file that contains all the information for the observation. But of course, all the fit image are purely fit images. Okay, so they are 100% usable. And when if I come back to David's presentation, David, you can take these images and process with your own system, and it will work. Okay, so they are perfectly standard. Okay, well, we need to have some useful information during acquisition. I already told that. We thought about this color coding system. For me, it's important. I know that when it is 3 EM outside, I'm not thinking the same way as during daylight, and I know that I can forget obvious things. And really, with Demetra, I'm sure that if this is green, so it means that I've collected all the data I need, and then I can go to bed. And this is something very important. We have included the logbook, which is very, very important. Keep some information of what you did, why you did that, how do you consider the data, and so on. And of course, we have to do the data reduction in one click because we have organized things before. Again, there is no magic. There is no artificial intelligence that try to understand what you did. This is very basic and very rustic, I would say. And but we really remain the full control to the observer. I don't want a software that you click and this is a black box and you say, well, Demetra made it, so it's good. This is not possible to work that way. You really have to, you remain, you are, as an observer, you are responsible for the data you produce and for the results that you publish. Okay. I think that's it. Well, it's free again. You can test it now, and all what I've shown you are in the IP version of Demetra with the demo images, so you can run to our Shediac website. And we have made some video tutorials, especially for the IP, that explain a lot of things that I've shown you during this presentation. And we also have a paper documentation. Well, maybe it is not exactly up to date, but anyway, it will help you. Okay, and I think that's it. Thank you very much. and I'm lost in time, Ken, but it should be not that bad, I think.
No, you're excellent, and it's good that you're done a little bit early because we have a lot of questions, and I'm going to start with one from myself, just because I don't quite understand something and I wanted to clarify. You have,
Yep.
It sounds like multiple versions of Demetra. So if I had an Alpi and if I had an Echelle, do I need to download two separate versions, or do I just click in that Dropbox and choose the Alpi or the Echelle?
Okay, so what we want to clearly tell is that there is one version for each instrument, and if you are using one instrument, you must use this version of Demetra. Now, when I've said that, technically speaking, the Demetra is exactly the same in all cases. And if you download the Alpi version, you will have also the Echelle version and the LISA version and so on. There are only two differences between the two parameters that are different. First, you will not download the same demo images. If you download the Alpi version, you will have the Alpi demo images. If you download the Echelle version, you will have the Echelle demo images. Okay. And the second point, which is a very small detail, it will select by default the instruments you will work on. I have shown you that how to switch from Alpi to Echelle. In fact, if you download the Alpi version, it is pre-set in Alpi, and if you download the Echelle, it is preset in Echelle.
Okay, and so if you were a person with two spectroscopes, then you would download two versions and just have them in separate areas on your machine. Is that true?
No, you can have the same. You can really have the same, and you can, I think you can even download separately the demo images. So if you have two instruments, you can download only one image. But now if you want to have the demo image for the two instruments, then it is better to download the two images. But at the end, it will be the same software. You only have one instance of Demetra on your PC.
Okay, all right. Then jumping to a question from Keith here, or a comment. He said it would be very helpful if Demetra, either in take spectrum mode or in manage mode, could give a resolution similar to ISIS or FHMW of the calibration focus.
Yes, this is for the next letter to Santa Claus. No, it will be done. Of course, we need to have it. It is quite easy to do in our case because we know exactly what kind of data we have. So we can do it. It is planned. Well, it is part of all what we want to do. Okay, so it will be done. This is the question that we have already received many times, and we'll do it.
Okay, good. The next one is from Valerio. I have a color camera, ASI 294 MC Pro. Did the software do the layering of the FITS files?
No, the question is no. So far, this is not the case, and well, we only take into account black and white cameras, and in fact, we go through the ASCOM driver, so we just collect image from the ASCOM driver, and so I think that for the acquisition it should work, but for sure we don't take care of the Bayer matrix.
Okay. Keith wants to know, is there a way to permanently change the initial parameters under scale and crop? They always revert to a set value that is not what I set.
Okay, so good, and this is an important point. When you have, if you do a first observation and then you set the parameters properly, you can at the end you can right click on your observation, and then there is one of the options which is to apply the parameters of this observation by default. Okay, so it means that from this time, all the next observations will reuse the default value that you have defined.
Okay.
This is something important at the beginning. In fact, you have the default values from Demetra. And then all the observations will inherit from these values. And you can change in each observation, you can change the parameters. But of course, if you change some parameters in an observation, you must not change them in the other observations. Okay, it would be very dangerous. So if you do that in one given observation, you do that only for this observation. But now you can say, you can tell to Demetra that now these values become the default values for the next observations.
All right. Thank you, Francois. The next question is from Richard. To copy the profile, after I run data reduction, I do a screenshot. Is there a better way?
Well, the profile of the screenshots, I would say it's a pity. No, I think that the best way is to use the output tab. In the output tab, you can generate clean PNG files, and with the dimensions you want and the information you want and so on. You can also generate them in PDF format. So I think this is much better than doing a screenshot, and the result will be the same, but in much better conditions.
Okay. Valerio wants to know, can Demetra be used with any spectroscope? I have a low spec 3 or just those listed spectroscopes.
That's a good question. One very important thing is that in Demetra, we consider that we are talking about one given instrument. Okay, and of course, we work to have our own. We are working hard to be able to support all of our instruments. Okay, so you can you can do it. You can use it with another spectroscope, but this is really at your risk. So I cannot promise that it will work perfectly because I don't know in detail these instruments. So I know the low spec, of course, but and I've never used it, and we have not done data processing reduction. Data reduction process for this instrument. So very probably it will work. And if you take the ALP 600 version, you may be able to adapt it. And especially if you have some calibration light or things like that, at one moment you need to have a list of reference lines to do the calibration automatically. And this line, you can edit it and adapt it. Okay, but this is really under your responsibility. So technically speaking, you can do it, and I have no restriction to do it. So I don't want to. This is important. I don't want to protect celiac against this. So if it can be used for the low spec, please do it, and I would be very happy. But maybe you have to. You'll have to make sure that you put everything under control.
Okay. The next question is from Richard, which may have been answered by Keith, but I'm going to go ahead and ask it anyway in case you want to comment. And Richard wanted to know, how can I capture a sequence of profiles that I got with Demetra over a period of time to compare them? And Keith suggested using plot spectra from Tim Lester, but do you have a comment there?
No, well, I think it can be a good idea. So for sure, the job of Demetra is produce a high quality spectrum. It is not to, we know that we could add hundreds and hundreds of functions to add element line, chemical element lines, to add, to compare spectra, to do mathematical operations and so on. This is not the job of Demetra, and for Demetra, we concentrate of how to operate as good as possible our instrument to make sure that we have a quick and high quality result. So this is the purpose we have, and we have not finished yet to work on that. So we are still concentrated on that. Now, if you want to yes, plot the plot spectra from Tim Lester is very good software, and you can also use Python, or you can also use Visual Spec, which is another alternative to take many spectra, compare them, do mathematical operation on them, and so on.
Okay, great. I was wondering if you're going to mention Visual Spec. Definitely a program people should take a look at if they're not familiar with it. Is the software using Vega and the calibration spectra to calibrate the target? And do you have to follow a specific order?
Using Vega and the calibration, I'm not sure to understand. So the idea is that you will have calibration images for each spectrum you take. Now, this is your decision to reuse the same calibration spectrum for all your images or to redo calibration images for each observation. So Demetra allow you to do both. Now the idea is that you have a calibration spectrum made with DLP in the case of DLP, and then the calibration is done automatically because the pattern of the neon argon lamp is automatically recognized. So I'm not sure to understand the question, but well, I guess that what you mean is that the Vega observation is the reference spectrum, and then after that you take the target spectrum, which is true. But in both the Vega spectrum and the target, the next target spectrum, will be calibrated with their own data. So in fact, you must do the target before in order to calculate the response curve profile, and then you will reuse the response curve profile in the next observation. So it's better to do the reference star before, but you can always do in the reverse order, and then you will process the target spectrum after the reference spectrum. Well, I hope I have answered the question. I'm not sure.
Okay, Stanley wants to know, what is the latest version of Demetra and what are your plans for it?
So the latest version is, I think this is the 5.1.6.7, I think something. Well, this is the one on the Sheliak website. We have a page dedicated to Demetra. And in fact, we are working. So this one is not does not contain the eShell processing. So if you want to have the eShell version, so this is not the official. It is still in beta test, so it's not publicly available. But if you want to have it, you can have it. And by the way, right now, we are working on the UVEX now, and so the plan is to have the UVEX version in the same timing of the UVEX itself. And well, I can tell you that this is a challenge. Well, now in a few minutes, we'll hear Christian and Valerie about how to process the UVEX data. And this is quite complex. Well, in the visible range, I think it is quite easy. It's very similar to LP and LISA and so on. But if you are going deep in blue or in red, this becomes a little bit more complex. So we still have to work on that.
Okay, I think that that's probably what we have time for right now, because we've got about 6 minutes maybe until the start of the presentation by Christian and Valerie, which will give you a couple of minutes if you need a break, because you've already just been giving a presentation, and you'll be introducing Christian and Valerie. Also, I noticed people are coming back into this particular session right now from some of the other breakouts. So let's just give everybody about 5 minutes here, including myself, to take a quick break, and then we'll be back in about 5 minutes to go ahead and continue with our presentation for the day.
Okay, see you in a few minutes.
Scanners are showing a window count. Expected duration, 9 minutes, 40 seconds.
Hi, my name is Heather, and I am an ambassador and volunteer with the American Association of Variable Star Observers. also known as the AAVSO.
Hi, my name is Anna Para, and I'm an ambassador for the American Associate of Variable Star Observers.
Greetings, Sky people. My name is Molly Wakeling. You might also know me as Astrono Molly, or by observer code WMOB on AAVSO.
Hi everyone, my name is Skylar Larson, and I'm an AAVSO ambassador.
My appetite to explore the universe emerged after binge watching Cosmos Space Time Odyssey in my mid-20s. And soon after that, I enrolled in my local community college and took a course called Astronomy 101. And after completing that class, that's when I realized I had a big passion for astronomy.
I'm a PhD student at University of California, Berkeley. I'm working on my doctorate in physics, and I've been doing astrophotography for about the last 5 years. And it's been just a real joy. I absolutely love doing it, and I'll probably never get tired of it. There's so many different things to do. After doing traditional astrophotography for the last several years, I've been wanting to get into scientific data taking, and I recently joined the AAVSO, and I finally got a rig put together of various bits and pieces to be able to take scientific data for the AAVSO and also for NASA's Exoplanet Watch program.
I am a beginner amateur astronomer. I'm interested in learning as much as I possibly can about our universe. And I'm here making this video as a member of the AAVSO Ambassador Leadership Team to explain to you what a variable star is. So what is a variable star? When a star, as observed from Earth or any observing point, starts to or has been behaving strangely over time, the first thing we notice is the star's brightness begins to fluctuate. The luminosity of that star is varying. The change in the emitted light can be caused by some pretty neat things. It could be a star swelling or shrinking, getting ready to explode its contents across the cosmos. We call that an intrinsic variable. Or there may be something partly blocking that light. It could be a cloud of dust or even an exoplanet, and causing an eclipse in front of that star. And we call that an extrinsic variable. Even our own sun, that thing over there, is a variable star. Its luminosity varies about 0.1% over its 11-year cycle. That's pretty cool. How do we measure a star's brightness changing? Well, by constantly observing it and documenting the magnitude. The apparent magnitude is what the star's brightness is. There's a scale there. Some stars vary over long periods of time and some really short. The data is used to monitor and predict what might be happening with that star. And if something really exciting is going on, the star will get a bunch of attention. Kind of like Betelgeuse recently, the second brightest star in Orion. It started to dim and do some pretty weird wobbly stuff into late 2019, but it has regained its brightness. We're still not 100% sure what caused that dimming, but there's been a few studies saying it's probably a cloud of gas, but I'm gonna let the experts look into that one.
Where do you even start? I started very early. I was a toddler when I started just stargazing with naked eye in my backyard, going to libraries to get all the books that I could possibly find on the subject, just researching about it on my own. And in high school, I was lucky enough to have the Boy Astro organization visit my school and teach a seminar about publishing a paper. Find your local astronomy community. There's bound to be a group of people in your area that study astronomy. Just get in touch. Nowadays, I am an AAVSO ambassador specifically for outreach and education. I make my own videos on astronomy topics that I like. As an MIT undergrad, I research centaurs right now. Centaurs are these little green dots, and they're like asteroid comet-like things. I'm trying to find satellites around them. But how exactly do I do that? Well, if you can't afford a telescope like I can't, I mostly specialize in data analysis. That's kind of taking images or data from a database that like somebody's already taken and kind of chugging it through some code and basically finding patterns in data. You can do this in a lot of ways. You can find light curves with variable stars. You can find light curves with exoplanet transits. You can try to find satellites going around solar system bodies, kind of like I am. There are loads of ways to contribute to data analysis in astronomy.
At the end of the Astronomy 101 course, my astronomy professor offered me a spot in her team to study binary stars, which I happily accepted. Binary stars are two or more stars orbiting a common center of mass. My research experience was very rewarding because I got to strengthen my research skills, I'd made new friends, and I was one baby step closer to understanding the universe. After completing my binary star project, I was able to jump onto a new research opportunity that focused on exoplanets, planets that exist outside our solar system. With the support of the AAVSO, I was able to join a team that focused on exoplanet transits using a transit modeling software called Astronomy.
Even you know the words.
My curiosity on exoplanets grew, and I found myself on NASA's website trying to answer some very important questions about exoplanets.
I'm going to show you my telescope setup and talk a bit about why I got into astrophotography and how I got into scientific data taking. So I'll give you a little tour of what I've got here in my backyard in the East Bay area of California. This is the science rig, which is the one I take my AAVSO and exoplanet watch data with. This is a Celestron CGE Pro that is mostly functional. It's unable to guide at this moment, but the nice thing with doing variable star observing is you don't need the best guiding, you don't need the roundest stars, just round enough to be able to register them. On top here is a 8-inch Vixen Newtonian f4 telescope, 800 millimeter focal length. I have an old Orion Starshoot Deep Space Monochrome Imager 2. I have a Starlight Express filter wheel that I have loaded with photometric filters, which is, you don't need to do photometry with AAVSO, but it's a type of observation that they like to get if you have those filters. And I have a RoboFocus focuser that I took off one of my other telescopes and attached to here, and it's been working quite nicely. One of the interesting things about doing variable star or exoplanet observing is that you don't actually need as high end of gear or as precision of tracking as you need for doing deep sky astrophotography. A lot of times the exposures are only 30 seconds, 1 minute, 2 minutes, not usually very long exposures like I would do for my deep sky. These stars don't have to be as round, and you want nice round stars for getting nice looking astrophotography, but for data taking, the stars can be slightly elongated, have odd shapes, things like that. The only thing that really matters is that the exposure is not overdone and that they're round enough stars to be able to register and align. So the requirements for doing variable star data taking is actually much less than doing astrophotography, which surprises a lot of people. The cool thing about taking variable star observations, either on your camera or even visual, if you're more of a visual observer, is that data that you take on the magnitude of that star on that given night, you can upload to the AAVSO website, and that gets collected into a database, and researchers can use that data in their research papers, and you can get cited in the papers, and it's a really great resource for the scientific community. You can contribute to the science doing, because on these bigger telescopes, they don't have the spare time to be taking data, but I've got all the telescope time I want. I don't have to dedicate it to other things. I run this thing doing variable star targets all night long, every night that's clear. So you can contribute to a wide variety of science right from your own backyard. And if you're an astrophotographer, you can do it with equipment that you already have. It can be really rewarding to see your data show up on the light curve generator on the AAVSO website, and getting the emails that say that my data was downloaded as part of the data set that a researcher was using. It's a real joy to be able to know that the images that I've taken on the amateur side of the house are also being used for science, in addition to the research that I actually do for my PhD.
If you want to know more about the organization and what our members love about this aspect of astronomy, or get involved with the Ambassador Program, please check out the website, www.aavso.org, and see what we're up to. Thanks.
Being a part of AAVSO has been a lot of fun for me. And I look forward to being able to share what I've learned about exoplanets to others and meeting folks who are curious about astronomy. So thank you for your time. Bye.
Clear skies.
All right, that was a video that our volunteer AAVSO ambassadors put together. They're highly involved in.
Your contract rolls on. There's some terms.
They're highly involved in outreach, and so if you're looking to get involved in outreach in AAVSO and you're a young astronomer, you can email me at lward@aavso.org.
And that is to an audit.
Sorry about that background noise there. I guess YouTube kept playing their next video randomly while I was talking. I didn't know once you ended a YouTube video, it just randomly chose the next one for you. So like I was saying, if you really want to get involved in outreach and astronomy education, that really is what our ambassadors do. Some of them are also involved in data mining and data analysis. And like Molly was talking about in our video, contributing observations to the AAVSO databases as well. And if you're curious about it or want to know more, just email me, lward@aavso.org. And I'm going to hand it back over to Ken and Francois.
Thank you very much, Lindsay. Thank you very much. Again, very interesting. And so we continue our workshop now. And we now have a presentation from Valerie and Valerie Desnoux and Christian Buil about the UVEX and especially the UVEX data processing. Well, I don't think it is useful to present you, Valerie and Christian, because you are all well known all over the world. And so just what I can tell you is that, well, we know each other. Well, I have a message, sorry. We know each other for a long time now. And you are people who are really changing the game. You have changed, both of you. You have changed the astronomy and the mainly the amateur astronomy, but not only. And by the way, of course, if you weren't here, Sheliak would not exist, and none of our instruments would exist. So you are somebody, both of you are guys very, very important to the astronomy, very important to me also. And this is really a pleasure to give you the microphone. And it looks like
François, can you hear us?
Video okay? Yes, I can hear you. Yes.
Yeah, it seems that we cannot start our video because the animator stopped it.
Really? Is it possible that we did that?
I just changed the setting.
Okay. Yeah. Okay.
Okay. So we can see you. We can see you, Valerie and Christian.
Hello. C'est ça?
Non.
Oui, mais c'est
yes. Yeah. Yes, we can see your screen. Perfect. The UVEX project.
Okay.
And again, Christian, Valerie, I will look at the questions, and maybe I will interrupt you for urgent question, and if not, we will keep the questions for the end of the talk.
Okay.
Hello, everybody. I'm happy with you
to be
with you, but my English is very, very bad, not fluent. So Valerie, present for me.
Okay. So thanks first for inviting us for this great conference. Today, the presentation of Christian will be over the UVEX project, the exploitation of this very specific new spectrograph, and some elements for successful data reduction. So in the presentation, we'll talk about the origin of the project, some very specific properties which make UVEX unique, the example of how to adapt for telescopes which are not the primary telescope which are targeted for UVEX, Very interesting information regarding how to use order filter to increase the capability of your UVEX. And finally, some elements of the acquisition, spectral calibration, instrumental response, flat field, and we'll end with some consideration regarding the camera choice, and again, the latest one. So on the origin of the UVEX project, you knew in the previous conference that it is a collaborative project which started in 2014 and which is a very, very public domain project where you can have the CAD files available as open source. It's a spectrograph which is specific in the fact that it is easy to find components. It has some high performance that are at the level that where you can do education and science. And the specificity is that you can not only address the blue part, but also you can go up to the infrared spectral domain, which are two new domains for amateur. And it is based on an optical concept where you can see the formula at the bottom here, which is a classical Czerny-Turner with a cylindric lens. All this is to correct for astigmatism and to have the lens capable to go deep in the blue part. And the project has been designed for 3D printing, as you can see on the right. Okay, so here you have on the left, I mean the group of the people who put some skills together in order to achieve these first prototypes and concept. The group of people is, we are in the French, right now we are in what we call French Riviera, which were between Cannes and Nice. So we call this group of people the Nice people or the nice people, which makes sense in English because they are very nice. Some are teachers in graduate school and engineering school. And all those skills around made this available, this printing version of the UVEX V3. And you can guess that after 3 versions of it, I mean, the group is still active to have some new ideas, especially around how to motorize the grating rotation, around some magnetic support for the grating to ease the removal, or even some micrometric for fine-tuning the focusing and so on. So we learned a lot. I mean, the group learned a lot, and there is a UVEX V4, which is already in preparation. You have some here preview of the new element that would come, and you will have an update of the files, again available on the website, where you can see here. And on this website, you can find all the video and all the tricks that could go with the CAD file that you can send to your printer.
Mm-hmm.
And besides that, if you don't want to print or don't have the capability to print to go by yourself, the beauty of this design would be available through Sheliak. That is coming, as Francois explained, by beginning of the next year. So let's talk about the UVEX property. A strange way to start with UVEX is what it is not. So what it is not, UVEX is not necessarily better than a LISA or an ALPI in terms of observation of faint object. It has a different optical formula that allows it to cover a very large spectral range from UV to up to IR, as we mentioned. But for faint object or for some resolution, you can. It's very hard to compare, and there is still performance that are achievable only with LISA or ALPI. But UVEX, besides this optical range, is also targeted to have a good flexibility of use, because you can change more easily the grating. It will have some better mechanical stability, and especially on the celiac concept, because it will not be 3D printed. So, it's expecting to have more robustness there. And it will have the capability to support a remote control for focus and the grating rotation. So let's talk a little bit about the UV property of UVEX. You know that it's a domain which is not very well explored from amateur and even for professional, because from the ground, from the earth. If you look at here on the black curve is a theoretical atmospheric transmission. And you can see on the ultraviolet part, there is a dramatic, strong attenuation toward 300 nanometers. And you can see here about what the current spectrographs are stopping here. And this is a gap we can still reach because you have some light, but you understand also that the atmosphere absorbs a quite fair amount of light. So it's going to be possible, but it's going to be tricky. If you look at if we make a zoom of the atmospheric transmission, there is an interesting feature here, which is what we call the hugging bands, which are the bands of ozone that you can, it's a feature, that pattern you can see here. And it's noticeable also on the real spectrum you're going to get from UVEX, because you can see them here, that really shows the performance of the spectrograph up to 320 nanometers, where you can even start to see the hugging bands. And this was a spectra of gamma cas here. So this capability is quite unique, not only for amateurs. I think it's not that very often that a professional has access to this blue part. And you can see in a spectra from this symbiotic star, very interesting line that very close to 300 and 340 nanometers here in this region. Very interesting to study, and I'm sure Steve Shore will be able to tell us more if we want on the physics of those type of objects. On the opposite of UV, we call it UVEX, but it could also be named IREX because it can explore, because EX is for exploration. It's exploration for infrared part. Infrared up to almost 1 micrometer. Yeah. And you have here two spectra. One is with Vega, and one is from quite Phi Persei B star. You can see interesting feature, not only the patient seriline, but also in the B star, you can see a calcium emission line, which are also interesting for doing science here. Last things to be noted on this is that it has been, those two spectra has been taken with what we call a reasonable modest size telescope, because it's a C8, because it's a C8 telescope. Quite well, Cassegrain is okay for infrared. So UV, IR, now the choice of grating. That's another capability of UVEX. So another two examples here with 300 lines per millimeter grating, and very small telescope. It's a Maksutov 120 millimeters. So with this grating, you can have all the spectra of the star, including the Balmer jump, up to H alpha here. But if you put a high resolution spectrum, 1000 lines per millimeter, and here you can see with Deneb that you can even better resolution and a very nice zoom on the Balmer jump to look at. And as Drew mentioned, I mean, some interesting way to do classification. Ouais. Tu veux dire quelque chose?
Très sharp, enfin, très fin.
You can see here that the line are very sharp,
constant,
and there is no distortion, no aberration as we go toward the green and the red. Yeah. Okay. So we said that UVEX is optimized for what we call small and medium-sized telescope. That means from 100 to 300 millimeters. And we say up to aperture of FD superior to 7. But really do not hesitate to think about UVEX on a small telescope. Here, I mean, we feature a spectra taken with this small Mach cutoff. And with low resolution grating and a reasonable slight of size of 14 microns, you can still have resolution power close to a little bit more than 1000. And there are two examples here. One is a star of Pisa, and below is the one with a higher grating of Vega. It's okay.
Okay.
You can also still observe some faint object with UVEX, and this is just to show you that if you take some example with the LISA spectra here, you can see, and you can see here below the UVEX spectra. Not exactly the same resolution, but you know, I mean, depending on the time you spend to accumulate some exposure, you can still reach a good signal to noise ratio. And it has some limitation, but can still some quite good job on observing a faint object. This is an example of a quasar with a Newton here. Yes, the feature here that you can see are the Lyman alpha feature line. Yes, yeah, which is redshift, which is a feature of allows you to measure the redshift of a quasar. So we've seen all the good properties. Now, I mean, a little bit of limitation due to this optical configuration is that there are some significant field aberration with the UVEX. So that means that this spectrograph is not well adapted for the observation of extended objects, like planetary nebula, or this type of galaxies, of large comet. Why? Because it's if you have some good focusing and sharpness here in some area and on the center, you can see that you have some blur from when you go from the distance from this center. And so that means if you have an extended object and when you want to do sky subtraction, if you subtracted sky on the part which are blurred, then you can see here that you will not correctly subtracted the line. So it's would be okay on the area around, I mean, on a specific zone, very limited in the field of view of the UVEX. So that's why, I mean, because of this, I mean, you cannot go with a larger object. We mentioned before that, yes, it is well adapted for telescope with an aperture of 7 and more. What if you have, like on this picture, a Newton or an aperture which is around FD4? So Christian has studied a way to, you know, still use all the telescope he has in the house. So, the Newton is very good for UV because it's all mirror surfaces. And he was looking at a Barlow that could do the job. You cannot put any Barlow. I mean, and so he looked at a different model. He found one that he put the reference here. That he also finds the optical formula. So he was able to run some simulation and make sure that the sharpness on the blue part would still be correct regarding the size of the slit. So, I mean, if you understand here the distance, so you know exactly where to put the Barlow. And this Barlow has very good apochromatism correction. And you can have on the right bottom here, the real image of the star in the 35 micron slit. So you can still have a capability to use an aperture down to f4 if you pick the right Barlow.
Yeah, it's sharp.
And you have at the bottom the example of this spectra with it's a Nova Cas 2020 with a Newton, a 10-inch Newton, and you can see the resolution and the sharpness from 360 nanometer up to almost close to the infrared. Obviously, I mean, putting a piece of lens is in the optical path will still have an impact on the blue attenuation. So because you see here, I mean, this transmission of the Barlow, even if it's good, I mean, it's dropping also at the blue part. So, I mean, don't think that you can still reach the same performance we have shown to you before with an FD7 scope, where you can easily have a good signal to noise ratio on the blue part of the spectra here. But still, it's a way to still use some telescope and do some good science. So let's talk here about diffraction order overlap. If you look at the first solar spectrum here, you would say, okay, very nice spectrum. I mean, I see the NA doublets here, and there is H alpha somewhere, and well, H alpha here, and that's atmospheric line. But I mean, what those lines are? And those lines are, in fact, the second order which overlap in this design. And you can see that there are the two lines from calcium, HNK line, which are showing here at double the resolution, in fact, compared to the order one. So that's why you have we recommend to put an order filter in order to make sure when you look at the red part, you only see the first order and you don't see the second order of the blue part overlapping. But if you think, and you can see here either the same effect, it's I mean, Christian moves the spectrum, the grating a little bit further in the red. So, but if you think differently, and if you take passband filter, targeted on the blue region. In fact, what you have now is that you have selected the order 2 only, and you have, without changing the grating, double the resolution. Of course, on a smaller region of interest, I mean, than the order 1 that you had having before. But here you have a portion of the blue domain, but with higher resolution. And if you wanted to do the same with an intermediate green filter, you can have a kind of zoom on the green section. And if you put a red filter, you can either have a zoom order 2 on the order 2 section without changing the grating, but putting a filter, passband filter in front of your camera, which is an interesting feature we found. An example of a way to do that, I mean, it's really to put a filter wheel between the UVEX and your telescope that can be manual or motorized. So that's a trick you can use with that increase the capability of the UVEX even with only one grating. So now let's talk about spectral calibration. Okay. So the way to do calibration, especially on the UV part, it's really not easy. And the favorite method, in fact, there is no really other way, is that to do it on the sky. You take a bright star, and you compute the dispersion law from this bright star. And the good things about UVEX is that the optical property is that the dispersion function can really be extrapolated towards the UV and the IR with a reasonable precision, and it is quite stable. So I mean, you can set your calibration law and then reuse it on the along the night with your other spectra. Or if you want to do it on the stars, there is no redshift, I mean no Doppler shift, then you can do that. So there is a tool in ISIS where you can have a pre-populated call for the Balmer line. If you click on the button, and you can see the result of the dispersion law, and you don't need to go further than an order 2 polynomial. I mean, it's a pretty robust design here. One trick that Christian recommends is that when you look at when you select the lines, it's better to do some rectification of the continuum. That means you remove the continuum of the raw spectrum. Because if you do that, then you have the flat continuum around the line, so you avoid some blended, I mean, some slope here. So your line center of gravity will be more accurate. There is also another way, which if you really want to be very, very, very accurate, if you want to don't use the star lines, and you are not afraid to put a lamp in front of your telescope, you can use an emission line lamp here, and you have some reference here that you can move at the front of the telescope, which create a spectrum. But you see, I mean, there is not a lot of lines, but if you mix that with a previous reference star, then you can have a very, very accurate calibration if you want to do some Doppler shift computation. Anything to add? No? Okay. Okay. So on the instrumental response, it's important to talk about this topic because, I mean, in UV, it's not as when you have a or a star. I mean, you need to have a reference star, which are quite emitting in the blue part. So what Christian found, and star where you have in a database some well-calibrated and well-known UV calibrated spectra. And there is a source of such a spectra that Christian found, which is the reference for Hubble telescope, GalSpec. And you can see here, he has taken some white dwarf star here, and he has taken an O-type star, and he was able to, using the GalSpec reference, to really compute the instrumental response, which are very good, even in the low flux of blue part. But if you have also to take into account that when you do such instrumental response with a reference star, you know that the atmosphere has a different behavior regarding the attenuation of the blue spectrum differently depending of the air mass. So there is a feature in this where when you do this instrumental response computation, you have a transmission model which is embedded into ISIS that can automatically correct, looking at the coordinates of the object in the fits header. It will take into account this and automatically adjust and compensate for the attenuation due to the air mass. So you can see without this taking into account the air mass, and after taking into account the air mass of the spectrum taken at different elevation. Another well-known issue, especially even more dramatic in the blue, in a UV part, it's the effect of the differential refraction of the atmosphere, and which can be barely noticeable in the blue part on an Alpium ELISA, but here on UVEX, or you go further in the blue, you really have to pay attention if you want to do some flux, have some flux accuracy. And you can see, I mean, you know, the refraction of the atmosphere makes a kind of a small spectra of your star. If your slit is perpendicular to the horizon, then you are sure in the slit to capture all the colors, I mean, all the intensity of your spectra. But if you put it a different way, and especially horizontally, you can have either access to the blue part, and you will have a spectra which will be more have some excess in the blue part. Or if you take on the red, then you have an underestimation on the blue part. So there is no unique way to compensate for that. First, you have to know that it exists, acknowledge for that. There is some specific well-designed atmospheric corrector which are suited for spectroscopy, so you don't take any one of them, I mean, without looking at specifically all the wavelengths and their optical design. Or you can use an Altaz mount, because in this case you don't have this field rotation. You have a field rotation, but it's well suited to put your slit. You can also have a mechanism to turn the slit, which is not sometimes very easy in all the spectrograph. You can also use a blue filter, or you can use what we call a photometric slit that we will show you in the next slide. Okay. So the photometric slit is a solution, in fact, to do two things. You can have access to your spectrum with a narrow area of the slit, which will be your resolve spectrum. But if after taking this spectra, you put the same star here in the larger slit, you will have, of course, a degraded resolution, but you will, as all even the small refracted spectra of the star here will fit into the larger slit. So you know that where you will compute the correct continuum using the traditional method of reference star, instrumental response, and so on. So in fact, with this, you can compute the real continuum of the star that you can apply as a kind of instrumental response to your highly resolved spectrum. So you will have combination of, here you will have the spectra out of atmosphere, well corrected, that you apply to your high resolved spectrum. Okay. Another pay attention here is that sometimes where whatever you do, even if your spectrum is very well designed, you can still have your telescope that creates some unfocus, chromatism, and you can see this type of profile of your 2D spectra. Pay attention, don't be too narrow on your binding zone, because otherwise here in the blue, you will you will not include all the flux in the blue part. So you will have some signal loss. So make sure you have a large binding zone. And for a very faint object in ISIS, always use, there is a box that you can click to select an optical Y binding algorithm for a very faint object. So that's 2 recommendations we have. Flat field, fine. Here, the flat field, to do that, today's actual calibration module of UVEX is not really compatible, as Francois explained. So Sheliak is looking at a new design and improved design, because we are really pushing the performance towards the blue. So it has to push the performance and some other components here. Christian today use which is une lampe, c'est quoi? C'est une halogène?
C'est une halogène lamp.
An halogen lamp that you manually turn in front of the telescope. Either you, if you are alone, or you ask your wife to do that if you are not alone. And you can have then this type of flat field. We've seen in the previous presentation from Laureen that she's also suffered of some fringe here. That's the same. Here you have some fringes. It's due to the detector by itself. You still not have a lot of good signals close to UV, but if you mix this one with a blue star, I mean, you can have, and there is a page dedicated. We don't want to go here into much details, but there is really a way to have a very good instrumental response, including the flat field, up to the blue, very far blue. But it has to be some combination of different methods here in order to really reach the maximum performance and the best signal to noise ratio on this blue part.
On peut dire que dans le bleu, le spectre est beaucoup plus lisse que dans le rouge, et donc c'est plus facile à traiter le bleu quand même que la compo lisse.
Okay. Yeah, regarding the fringe here, I mean, you don't have such fringe in the blue part. So if you only focus on the blue, not too much on the red, here you are very clean and very flat. I mean, not disturbed the spectrum. It's more easy to calibrate here.
Yeah.
Some picture here of the type of lamp. It's not easily to find them currently because they are disappearing. So you have also some temperature of daylight lamp that are some used for museum, because they have a way to very neutral way, temperature which is very neutral to best show the painting. We'll end with a few slides regarding camera and that Christian studied recently. You know, I mean, that detector is of course a central element of any spectrograph. You have more and more new CMOS camera that come on the market. The CMOS is good because you know that it has a lower readout noise. It has good quantum efficiency, so both of them are important for spectroscopy. But the bad news is that, and it's less costly for the same size of a chip. The bad news, I mean, you have very small pixel size, but it's sometimes not very well adapted to our current spectrograph. And you have some amplifier glow. Even if on some chips it's recently fixed, but it's not very a problem. If it's static, it can be easily removed. And you have a new structure of noise that's called random telegraph signals noise, RTS. But I mean, even if it's new, I mean, there is a mathematical way to reduce those noise, and we'll see that later on. So about this telegraphic noise, so you can see it's a non-Gaussian noise that appears at the pixels and can pop up. We call people also call that salt and pepper noise. It can reduce the detectivity of the faint object and by limiting the magnitude that you can see, and it can add some possible artifact, creating some false detection. So it's compared to the CCD camera, it's a new noise you have to take into account. If you look at the two latest sensor, I mean, Christian compare here, you have the sensor of an IC 183 here, and the latest sensor, another sensor, which is the one which equipped the 294 ASI here. You can see that if you look at the histogram of the noise, you can see that even if the noise is quite good, I mean, quite good, better here than here, you have an histogram which have a dispersion which is larger here. So based only on the consideration of effective global noise, we could say that this sensor is not as good as the one of the 183 one. But there is a way to compensate for that, because of the small pixel size of the CMOS. I mean, your spectral image today is very is oversampled, and that means that for same wavelengths, you can have several pixels that sample the wavelengths. So you can really do some noise reduction by doing some median computation in order to preserve, and you will not degrade the spectral resolution, but you will decrease the noise. And you can see here, if you take the 183 histogram of the camera, if you do a binding 2, you can physically decrease the dispersion of the histogram, and you can see that the noise is reduced. In this, Christian developed a new algorithm, which is a CMOS median, which is also calling it CMED. We'll not go through the different steps here, but you can see that the original noise structure, and after all the processing with median filtering, with other Gaussian and reduction of the image by binding, which is optional, you can really drastically reduce the noise thanks to the oversampling capability of the sample. You want to say something? Tu veux dire quelque chose? This is a tool here in this. You can play with the different filter strengths or optional binning and so on. So you can even take a dark image and play with it to see the effect on it. We'll not talk about the way this is a way to compute the sampling sampling factor of your spectrograph. You can have here the result. If you compare the two sensors we described it before, you can see here that if you have the different camera here, you have the different feature, size, gain, readout noise, at different performance. You can have the quantum efficiency. Christian define what he call a figure of a merit function with what he call D star, which is proportional to the quantum efficiency, but inversely proportional to the readout noise. And F is
factor binning.
The binning factor. Thank you. So something. And the most interesting probably is this table here. You have a different configuration of the sensor. If this is a traditional camera with a 244. If it's compared to the 183 not binding, the pixel is smaller. So, I mean, naturally, the merit is a little bit lower. But if you apply optical binding plus the CMED and so on, you can see, because it's really over something, you can play with that. And then you can still recover the performance of the ASI 240. But if you also apply, I mean, compared to a non-standard non-binding. So, I mean, if we look at the D-star factor merit function, you can see the two cameras are quite equivalent. But clearly the 284 offers a larger spectral coverage, which is interesting in using UVEX. And you have also some better and blue and red quantum efficiency. So there is no yes and no. It depends also of the type of slit, the type of work you would do. If depending of the size of your slit and the capability to oversample or not, then you can either choose. I mean, you have two choices, and maybe this camera is better for a small slit because it oversample a lot. So you. And maybe this camera, it's to be a good choice with a larger slit with your telescope. So, I mean, that's not black and white.
La frontière n'est pas si claire, mais c'est comme ça.
Yeah.
Okay.
So, this will end the presentation.
Thank you, Valerie.
Wow. Again, what a presentation, and I've loved the rainbow in your eye. Thank you very much. Thank you very much for this presentation. And it's, well, for me, it says that we have a lot of opportunities in front of us, and also we have to be very careful to know how to manage that and to process the data properly and so on. That's very interesting. I don't see a lot of questions around. Maybe. Oh, there is a bravo. There is a question, yeah, just arrived from James Lee. Does the CMED process, is it available in the ASIS 6 version?
Yeah.
Yes.
C'est une nouveauté de la version 6.
This is why he made a new.
Principal nouveauté.
Okay, so this is the main reason. This is the main reason for the version checks.
Yeah.
Okay, perfect. And we also had a question before that was about the flat images. Are there? The question was, when you are doing flat images, do we keep the grating in the light path?
Quand tu fais des images de flash, est-ce que tu laisses le réseau dans le chemin?
Well, I suspect this is somebody who comes from astrophotography and who don't really understand how flat works.
Je veux dire que quand on veut faire un flat field, il faut toujours avoir le même chemin optique entre ce qu'on a fait sur les étoiles et ce qu'on a fait. C'est la règle d'or en fait.
So I mean, yeah, but if you come from astrophotography or photometry, you know that it's very important you have a consistency in the light path. So whatever calibration you do, even in fact for wavelength calibration, it's important that all the optical elements you have are the same all along the different flat field calibration, wavelength calibration, flat and so on. It has to follow the same optical path, otherwise you are not compensate for the defect of your instrument, in fact.
So you have a thank you from Woody for your talk, and also, well, there is a question from Nick who can saying that the CMOS comparison is very useful, and can you make available the PowerPoint presentation? Well, sure, it will be.
Yes.
I guess, and maybe can
also Christian has a web page on his site.
Yeah.
Okay. So,
and the PowerPoint will be available. Yes.
Yeah.
Okay, so the PowerPoint will be available on both sides, and well, you have a merci from Nick, and maybe Ken, you will tell us how all this data will be available and when, and so on the AAVSO
Well,
website.
all of the presentations have been recorded and will be available to everyone. I don't have the timing for it because this weekend was, well, last weekend was the first part of the spectroscopy workshop. Then this weekend we have the main part. Next weekend, the AAVSO has its annual meeting. So there's a lot of work that's being done for that meeting. But in the next near future, all the presentations will be available on the AAVSO YouTube channel. So people will be able to see all of the presentations again if they want. So no problem. I will put in the chat box, or Christian and Valerie can put in the chat box Christian's URL for his website, so people can find the slides out there as well. And then I had one quick question to ask of Christian and Valerie, and that is, we saw information about CMOS cameras, but if somebody still has a CCD camera, how good is the CMOS versus CCD with the UVEX? Let's say maybe a 460 EX camera.
Quelle est la performance d'une caméra CCD? Parce qu'on parle que des CMOS, mais une caméra, une ATIC à 460, est-ce que c'est performant avec un UVEX?
C'est une très très bonne performance en vérité, mais les composants sont plus petits. Et ils deviennent rares maintenant de plus en plus. Donc c'est vrai qu'une caméra, moi j'ai le premier spec que j'ai fait, c'était avec une DCCD, ASI 414, 460, c'était très bon. Mais aujourd'hui, je privilégie le CMOS parce que c'est devenu la base.
Oui, d'accord, mais pour quelqu'un qui a eu...
Oui, pour quelqu'un, absolument, absolument. Okay.
So, I mean, it just confirms that before he used CMOS, he was using an ATIX 460. With very valuable camera to access to the performance of UVEX. There is no need to have a CMOS camera to have the performance of the UVEX. It's just because they are new camera and he likes to work with them, and it's a large sensor, so it's more comfortable in fact. But you can, there is no problem to use your ATIC, whatever, CCD camera.
Yes, yes, yes.
Okay. All right. Thank you very much. You know, I thought that this was a fantastic presentation. So much information, very valuable comments and information. And I think I speak for everybody in the spectroscopy community when I say that we really appreciate all the work you do, analyzing the different cameras, analyzing and figuring out how to make different telescopes work, coming up with the design of new spectrographs. It's just incredible. And we really appreciate it. Thank you very much.
Thank you.
Bye-bye. Thank you, Ken.
Thank you.
Bye.
Okay, so next up for us is the Steve Shore's presentation with Woody Sims, but we're going to handle this presentation just a little bit differently because it's the last presentation of the workshop, which gives Woody and Steve a little more flexibility than the other speakers have had, and they'll be able to actually go over the time limit if they need to, and I'm guessing that they will, because we've had a lot of questions last weekend and this weekend on astrophysics topics. And you know, you couldn't ask for a better expert than Steve Shore when it comes to astrophysics. He's incredible, and he's also an amazing friend to the amateur spectroscopy community. So this is great. So before we started in on Woody and Steve's presentation here, their conversation as we're calling it, I wanted to take the opportunity to thank everybody for attending this workshop. We had a great time, all of us that are presenters and were involved in it, but it did take a lot of work. So I'd like to thank all of you, first of all, for attending. I'd like to thank you for putting up with me. This is the first time I've ever done a webinar, let alone a 4-day webinar. So I appreciate your patience that you displayed throughout all of this. And I also appreciate the incredibly hard work that was done by the AAVSO and the AAVSO staff to make all of this happen, because without them, it wouldn't have happened. So they're an incredible bunch of people. We all deserve them a big round of applause, which given the circumstances, we can't do very well, but just suffice it to say that they're an amazing group and we really appreciate it. And with that, I'll turn it over to Francois, who might have some parting words, and then I'll introduce Woody and Steve. By the way, Francois, you're muted.
Yep. Okay. So let's thank you, Ken, and I also want to thank everybody that make this this meeting possible. So we can see you, Woody. Woody, we did introduce you yesterday, and you did a wonderful talk about how to organize your sessions. Now, if I can give a few words about Steve. I don't know how to introduce Steve. Well, he became a very good friend, somebody very important. Steve is in Pisa in Italy, and he is a teacher at the Pisa University. He's astrophysicist. He's one of the editors of the ANA journal. So somebody who has a very wide knowledge. And Steve, you came at our OHP meeting for a few years now. I think maybe 4, 5, 6 years. I cannot remember exactly. And you did share a lot of time with us, sharing all what you know, which is just incredible, and all the passion you have for all the stars, all the old friends there in sky, like you often say. So it's really a pleasure to work with you. I'm always impressed because when you talk, you have no preparation. So most of the presenters that did participate to this workshop spend some time to prepare things, and I'm not sure that you even know what you will be talking about now. But I know it will be fantastic, and I also know that working with you in an interactive mode with Woody is by far the best way to talk with you and to learn. And I'm sure that everybody online would love to interact with you. So Woody, you are very, very lucky, and please don't hesitate to interrupt him and make something live, which is the best I've ever heard. So thank you very much to both of you. And as usual, Steve, you know that we keep an eye on timing, but I know that I will never success in any time control with you. So well, now it's night in France. So thank you, Steve. Thank you, Woody. Go on.
And before we get started with their conversation, I just would like to point out that we will be back next year. We have every intention of doing an in-person spectroscopy workshop in the Boston area at the beginning of November in 2021. So I'd like to ask everybody to try and keep that time period free on their calendar. In the meantime, there will be more activities with the AAVSO. This has been a good experience for us doing a webinar and using Zoom for something like this. And it's opened our eyes to the possibilities of things that we can do in the future. So there'll be more activities like this. This is not the last one. And hopefully we'll have an in-person meeting next year as well. So with that, I'll turn it over to Woody and to Steve for their conversation, unless Lindsay has something to say first. No? Okay. All right. So here we go. Thank you.
Okay, well, hi, everyone. My name's Woody Sims. You probably suffered through my talk yesterday. I hope you're still interested in spectroscopy after that, and maybe even able to get better quality scientific data. I'm going to introduce my friend Steve, and I'm going to share. Francois indicated we may not have prepared a lot for that. That might be an understatement. So there's no fancy PowerPoint stuff here, but I wanted to, can you see this, reading nature's fingerprints?
Yes.
Your hand. Steve gave up the title for this, and I thought this was absolutely fabulous for spectroscopy. But I want to take just a minute to add to what Francois said. Steve is a professor of astrophysics at the Universita di Pisa, in Pisa, Italy, and a great friend to all of us small telescope scientists. And that's a term I think Steve prefers to call us over amateurs. I first met Steve virtually through his writings that conclude each issue of the Eruptive Stars Information Letter and through numerous astronomers' telegrams. Then I had the good fortune to attend OHP in Provence, France, and met Steve and many of the speakers in person that are in this workshop. And I'm just gonna pop to the next slide here. I love this picture. You'll recognize, of course, Francois Cochard, Steve, Francois Tessier, myself, David Boyd, and the famous Paul Lucas from Perth, Australia. What a gang. What a lot of fun. OHP is a fantastic event. Earlier this year, I had planned a ski trip to the Italian Alps with my Italian friends who live in Vercelli, and Steve invited me to come to Pisa. A 6-hour Sunday afternoon chalkboard session with Steve on novae, accretion disks, symbiotic stars, red giants, solar winds flashed by like it was only an hour. It was probably that session that gave us the idea for today's workshop. Let me go to the next slide here. So just a bit more. I just picked a few highlights. Steve was an editor of the Astrophysical Journal, and since 2003 has been one of the scientific editors of astronomy and astrophysics, and I know he takes a great deal of pride in that. Steve was on the Goddard High Resolution Spectrograph Science Team for the Hubble Space Telescope. Before that, an associate scientist at the BLA in New Mexico. And he's the author of numerous books on astrophysics and history of science. And all of these, as I've said, they're available on Amazon, but I just picked out a couple: The Tapestry of Modern Astrophysics, Astrophysical Hydrodynamics, and Introduction. On the historical side, Forces in Physics, a historical perspective, and the most recent book with Louis Magnani, pronunciation adjusted, A Dirty Window, the Diffuse Interstellar Medium. And I've started reading that. And one of the many things, but Steve writes so clearly that you almost think you can understand these very difficult astrophysical concepts going on. So Steve, I guess I should give you a chance to say something before we go into the questions.
Could you stop this?
Okay, I'll stop it. All right. This is what Steve likes, okay? And Steve asked that I not brief him on these questions in advance. So Francois, you guessed correctly on that. So
there's no teleprompter.
And no teleprompter. So
and I promise that that'll be the last political comment.
Okay, you did promise me. So I kind of combed through questions from this workshop. And so this question came up early in the workshop. If all emissions come from electron transitions at a given wavelength, then where does the continuum come from?
That's a neat question. That's a really neat question because it goes back to an essential feature of radiation. Remember that you guys are measuring light, which means there have to be charges accelerated somehow, or changing electric fields, changing charge distributions. to produce an emission. So when you see a photon, whether it's from a transition between bound levels or a transition from a continuum of levels to a bound level, or even a transition, this is not hard at all, a transition from a continuum to a continuum, just a collision, an inelastic kind of collision, then light will either be absorbed or emitted in that process if it's between charged particles. Neutrals, those things which are inherently neutral and structureless, which really exists only in theorist dreams and elementary physics books, those don't emit. They may produce gravitational waves, but they ain't going to produce photons. So what you're seeing whenever you're measuring light is either, if it's a discrete emission, that is, it has a characteristic wavelength and perhaps an interval around that, that's coming from some kind of a bound to bound transition. Okay, let me try an example. Can I do a shared screen here? Let's see. Okay. Now, I hope you can all see what looks like a blank screen.
I can
see it.
Okay,
yeah,
so
by the way, Steve, your mic is moving across your shirt, I guess, and then we have some noise due to your microphone, which is not very easy to understand. But if you can do something, but
well, I can try to just hold it and play journalist here. I thought this wasn't what was registering, but okay, is this a little better?
much better.
Okay, so imagine here that you have a nucleus, just a bare proton or an atom that's been ionized, and it's surrounded by a sea of electrons. Now, these are a little bit like sparrows compared to, say, a whale or minnows compared to a whale. The mass ratio being a couple of thousand between a proton and an electron. The electrons are mobile with very high velocity at the same temperature as the protons. So you can imagine this heavy thing is just fixed. Now, the way that one conceives of the emission is that if you were to have an incident electron, it would be deflected in the electric field around this point charge, and the result would be the emission of light. Now, there's nothing in particular that says what this energy has to be. The average deflection, because the average incidence is going to be at very large distance, the average deflection is going to be really, really small. And so you would expect that most of the emission would be at very low frequency. There wouldn't be much of a change in the momentum of the electron because it's a distant collision. But once in a while, you're going to get a close approach. And in that case, those are going to be large deviations, large changes in momentum, and the frequency of the photon that's emitted is going to be higher. Okay, but it's a continuum. There's nothing that says these are discrete levels. Okay, so far?
So this would be visible to us with our spectrographs in the visible optical range?
It can be. It depends on the temperature. It also depends on the density. First, the density contributes two things. First, that just because the electrons have an opposite charge to the protons, there's going to be a sort of shielding. That is, a particle, little bugger out here, doesn't just see a bare nucleus, it sees the nucleus kind of through a fog. And so the effective charge actually seems to change as it goes inward. Now, that depends on the density and it depends on the temperature. So the amount of deviation is going to partly depend on the physical conditions in the medium that's emitting. Now, if the temperature is high enough, the particles are, the electrons are moving at high enough velocities, better. They've got energies of about an EV, an electron volt, if the temperature is about 10,000 degrees. What that means is their average energy is about the same as an infrared or optical photon. So if that changes, if they're deviated and they emit, they're going to emit in the optical or in the infrared. The hotter the gas, the closer it's going to be to filling the optical window. Okay? So if you're looking at a nebula, just low density gas, no self-absorption, temperature of 20,000 degrees maybe, because it's got a hot source in the center, then you're going to see some of this radiation. It's just thermal radiation from the deviation of the electrons. Best way to imagine it is it's a little bit like driving on, it's like driving on a highway in a rational country or Italy. In a reasonable country with a low speed limit, you know, like driving in the city, if you have a collision, the parts from your car aren't going to go very far. You know, the energy that you emit isn't going to be very large. If you have a collision on the autostrada, you're going to be spewing at fairly high energy. Okay? It's basically the same thing here, that the higher the temperature of the gas, the higher the energy of the emitted photons, because you have more energy to tap. Now, the other thing about this that I hope will be clearer is that this is a way that the gas loses energy. If you see the photons, the medium is emitting them. It's not that they're coming back after you've used them up to make your spectra. It's not that you're re-emitting them and they go back to the atom. So a gas that, for example, has undergone this kind of emission because of collisions is cooling. This is a pretty inefficient cooling mechanism, in large part because it's not resonant and the bulk of the emission is at very low energy. But it nonetheless changes the physical conditions in the gas over time. Okay? That makes sense, I hope?
So if we had an A star continuum and we compared that to an M star continuum, we're going to have quite a temperature range there. Maybe you can kind of tie this back into to the difference between those.
Okay, now this gets to a different kind of question, but it's important. When all of you say continuum, and this is a disease of the business, what you think you're saying is that point which is in the wavelength range you're looking at, in that part of the spectrum, so transparent that you're seeing through whatever the atmosphere is to the point where the surface is essentially opaque. Unfortunately, in an M star, there's really no such thing. You aren't ever seeing the part of the star that's producing this kind of spectrum. You're not seeing the part of the star that's actually emitting or absorbing principally in the continuum or by continuous processes. In an M star, at the resolutions that most of you are working with, anywhere from ALPI to even the E-shell, you're not going to see down to that part of the surface that's so opaque that and so hot that the lines aren't contributing at all to the opacity, these bound transitions. And you're actually seeing the most optically, as we would say in the business, optically thick part of the surface. The reason for that is that any portion of a gas, I mean, let me go back to a point I tried to make a moment ago. if you're seeing the photons, they're being lost from the medium. So if a part of an atmosphere is, say, transparent, or a little more transparent than a lower depth that might be more compressed and more opaque, the outer part is also effectively cooling, okay? Now this means several things in the physical state of the gas. If it were ionized, it's very likely to recombine. If it were excited by collisions, it's very likely to not be effectively excited anymore. So rather than emitting, it's going to be principally absorbing and scattering. And that creates a kind of opaque screen, which, if it's opaque enough, you can't penetrate. So what you're really seeing is kind of the upper atmosphere, the colder the star is, okay, in the range of stellar spectra that you're used to, like an A star versus an F star versus an M star. In the M, the dominant mode of absorption is from molecules. Not because they're the only things there, but they're so damn deficient at absorbing, especially the hydrides and the oxides. So titanium oxide, zirconium oxide, vanadium oxide, the bands that produce the characteristic appearance of the cool stars, the coolest stars, are incredibly powerful absorbers. They're vibrational states. That is what you're seeing. You know, I'll try not to make extra noise here, but what you're seeing is the molecule. Well, here, going back to this, you have in some of the oxides, like, let's say titanium oxide, if you just think of this as a diatomic molecule, there are many modes that this has for emission. One is that it can have a kind of rotational transition. Now, this isn't classical rotation, but it's that you're taking this charge distribution and whirling it around in a way that produces emission, typically at far infrared wavelengths. But there's also a mode, because these nuclei, the oxygen and the titanium, are, and this is the strange thing about molecules, they're physically separated from each other in space. They're separated by about half an angstrom. So there's an electron cloud between them. It kind of looks, if you want an example, like two balls surrounded by cotton candy. And these, because they can repel, can be set into vibration, in which case they are two charges that are vibrating and emitting. The energy required for that is sort of optical and near infrared. And then there are also transitions for the electrons. So the size of the electron cloud can physically change, exactly like you have in atomic transitions. Okay, so you have three different types of transitions, all of which have different energies. The rotational states dominate the far infrared and also the millimeter. The vibrational states can be as high as the ultraviolet. And then there are the electronic states that govern the energies of all these other transitions. I don't mean that to be difficult. It's actually quite simple. You just think of how many different ways, if you had a slinky or spring, how many different ways can this move? If it's just two atoms, which are the dominant components in a cool atmosphere. And all of these bands overlap. I don't mean that all of the titanium bands overlap, but those of titanium oxide are not the same as carbon monoxide. And so, since they're in the same gas, they're all absorbing. As far as you would think, this is a continuum. You wouldn't see anything but a few high points. And you might very well draw a line there.
So do those high points represent what we would think of as the level?
It's better to say physically that this is as deep as you can see. You can't see any deeper than that. But it doesn't say that you've reached a surface which is actually coincident with what you would call the stellar radius. I'm making this more difficult than it needs to be.
And well, Steve, this ties in really nicely, I think, with the next question. And
yeah.
Maybe we continue and answer that one, but do different wavelengths of the continuum come from very different depths in the star?
Okay, and an example that comes to mind immediately is something that is very kind of COVID related. Think of taking an infrared picture of a person versus an optical picture, and let that person have sort of a hairline of some sort. I don't care about the gender. In the optical, especially, take a picture. Take a picture of someone on a bad hair day. Okay, their radius is going to be enormous, depending on how bad the hair day is. On the other hand, if you take it in the infrared, their radius is going to be that surface which is opaque at all wavelengths. You're not going to necessarily see much from the hair. Its opacity isn't very large at that wavelength, and it's not either a strong contributor to the emissivity, okay? Mm-hmm. So the radius depends immediately on how large the emitting surface is. This is a real problem in stars, actually. It's one that I've, over the years, tried to emphasize in other teaching. The radius of a star is a concept that we have from billiard balls and soccer balls and basketballs, and it's not appropriate. It may be for a planet like the Earth, where you have a phase transition. Okay, so you've got a solid, or you have the ocean, which is a liquid, and then above it you have an atmosphere of a very, very different density. And so you can say that when you're falling, you've hit a surface, okay? And that is the radius of the object, because you don't enter into it. If you did the same thing on Jupiter and took the surface that we see, you'd fall right through it. That surface is simply opaque. Perhaps the best example I can show you, if I can bring it up quickly, is typical of here.
We're still seeing your tablet.
Yeah, I need to figure out a way of changing this. Okay, new sheet. Okay, but you can see this now.
Yes. Yes.
Okay. It's a kind of good day on the Arno at this time of year. That is the surface of a star, people. That is, you know damn well that behind this, there's still a road. What you don't know is that here there's a river. Okay? But you see, you can see kind of, sort of something here. But then beyond it, you have no idea what might be there. So if you started swimming here, you would see in front of you this. No matter where you are in this fog, you see to precisely this distance. Okay? As you start walking down this road, you're going to see that there are buildings over here. But then if you turn around, you may not be able to see these anymore. That's what we mean by opaque, optically thick. Okay? There's the surface. It's when you take any opacity, it doesn't matter. Here it's droplets. It's in fact a continuous opacity because it's from an aerosol. okay? If this were not condensed into an aerosol of droplets, you'd see perfectly. You'd see all the buildings, you'd see the Ponte di Mezzo, you'd see that there's a bridge here, you would see the other side of the river. But here, you don't see any of that, okay? So when we talk about the surface, in this case, this is the optical surface. Now you can ask, what about radar? Well, that's centimeter wavelengths. Okay, it's microwave. The cars that are in this part of the fog, ask yourself, can they listen to a radio? Because if they can, this medium is transparent. And yet when you're driving through a tunnel or you're going underwater in a tunnel, there's a point where while listening to, say, FM radio or AM, you don't hear it anymore. And then when you're coming out of the tunnel, there's a point where you can hear it again. You hope that when you look up out of the car window, when you're really deep under the water, you can't see the sky, because in that case, you'd be in trouble. But your radio, if it's absorbed, if the electromagnetic radiation is being absorbed by the intervening medium, is going to be, it's going to be the same as the light that's emitted in this fog. It's going to be attenuated. And the attenuation depends on the frequency. So yes, the radius of the star depends on the opacity of the medium above any depth to which you can see. Another way of saying this, that perhaps you can all burn into your heads, because this is valid for any transport of radiation. You always see into a medium up to the point at which it's opaque, which is a very technical way of saying you see as deep as you can, but you don't see any deeper. So if you had a microwave, you could see straight through this medium. If you had radar, you could see through this medium. And in fact, if you couldn't, you wouldn't use radar in landing a plane in the fog. Okay, but in the infrared, in the optical, no. In the infrared, you can see a little bit deeper because the wavelength is larger than the size of the average particle in the aerosol. But it's not going to be infinitely transparent.
So then the answer is to that question, again, the question is, do different wavelengths of the continuum come from very different depths in the star? The answer is yes. And if you expanded that outside of our optical spectroscopy range and you went to radar frequencies, you'd see even deeper.
And in fact, we do. This is one of the ways that you probe the outer parts, say, of the wind of a star, because the densities are very low, but the volumes are enormous. The temperatures are moderate. And so you don't see that in the optical, but you can see it in the radio.
Mm-hmm.
And for example, you can form images, just like H2 regions, just like nebulae. When Pascal and Olivier were talking about planetary nebulae, and when Francois was talking about symbiotics, it's the same thing. That in a continuous process, the emission is going to be, well, continuous. And so you may be able to probe in the optical some region that in the ultraviolet is opaque, or in the radio, some region that in the infrared is opaque. And then between these regions, you build up a three-dimensional picture of the atmosphere. Now, let me try a cartoon here. So going back to here, that what you see when you're looking into a medium and I'll call this an atmosphere. So it doesn't have to be a star. This can be an exoplanet if you want. It's the same thing. It's really just a question of where the light's coming from. You know, we imagine in the spectrum, so the sorts of things that Valerie and Christian were showing, that you have something that looks like this, which is something you might see in your dreams, where this is the flux and this is the wavelength. And so you have a series of lines that are absorbing or scattering, but that are attenuating the light. And you also have a portion here where there's this discontinuous change in the opacity, that here you would think, okay, the surface is getting brighter, so maybe it's because the opacity is diminishing. It's not that it's uniform and here it's more absorbed and here it's less absorbed. But this jump, this discontinuity, which in, for example, Vega or any star with a temperature greater than perhaps 8,000 Kelvin, Vega being about 10,000, this jump corresponds to an absorption that does this. Now, in this case, it's the same thing as imagining energy levels and ionizing a system. The example that comes to mind is one I think actually makes this a lot easier. You think of stadium seating, which now would require social distancing, but you imagine that social distancing determines how many people can be located in each one of these rows, and that there's a limit to where these rows stop, okay? In other words, there's some maximum level here. Now, this height that is between the first row and the last row corresponds to a kind of binding. We imagine that the only way you can get out of here is that you have to walk up to the top and then kind of exit. Okay, so everybody, I hope, has this cartoon in their heads. Given the size of the row, you can pack a certain number of people into it, and in the completely filled equilibrium state of the system, these are going to just be populated levels. And the lowest energy is obviously the first row. When that fills, you go to the second row. When that fills, you go to the third row, and then you eventually exhaust the number of people, or in this case, the number of electrons. And that becomes your state. Now, if somebody comes along...
This step down ramp you've got, that's the ionization state?
We're going to get to that.
Okay.
Okay. That we're just going to say that the only way you can get in or out of this quietly is through the top level. Okay. Okay.
Yep.
Now, you have somebody with a really weird sense of humor who puts charges under these seats, and one of these characters gets promoted. Okay. It might be from the front row, it might be from a back row, it doesn't matter. You have one person less. Okay? As long as you exceed a certain energy, that person is going to be bounced out of the system. But anything exceeding that energy is going to bounce the person out. There's merely a threshold. Okay? That's ionization. That's the most elementary continuous process, because that will happen in a gas that's neutral. It just has to have the energy supplied somehow. There are two ways of doing that. One you'll see and one you won't. if it's being performed by photons, then the photon that caused this is no longer available. Okay, and so you're going to see an absorption. And since the most efficient process is going to occur threshold, in other words, right here, the opacity of the medium, the absorption, will decrease as you move away from that, but always on the higher side. So you first see an almost discontinuous change, and then there's a recovery. In this case, the recovery may not be as rapid as it is here. Okay? A continuous opacity, in other words, would produce something that looked like this in its ideal form, where this is the wavelength and this is the flux. Okay, and since you can get rid of someone from any of these levels, there can then be reconstruction of the system, that is recombinations, or there can even be transitions. Somebody from an upper row says, hey, there's a free space, and drops down to the lower. Okay, so we can have an ionization followed by an emission process. Mm-hmm. This is what makes it a little bit more complicated than the kind of cartoon textbook image. Atoms have multiple electrons, with the single exception of hydrogenic species, because they have only one electron by definition. But as soon as you have multiple electrons, you have a gazillion possible combinations. So all of those can produce absorption and emission, and even couple so strongly that one of these in leaving may excite another into an excited state, or one into a lower state. Okay? That's the ionization process. The inverse of that would be that an electron arrives precisely at threshold, okay, right here, and then rolls down in each one of these steps. So to go now to a new screen. So in each one of these steps, or this step, or this step, all of those are possible. All of them are continuous processes originally, because you're going to a particular energy level. And then the process of cascading downward, so produces, for example, in hydrogen, the series that would be the bracket to Paschen to Balmer to Lyman, okay, as a series of lines. Okay, that's it. That the reason for these emissions is because you have the inverse process, and you always can have that because that requires the lowest energy of the interaction. That is, particles that are moving a little bit too slowly can be captured. Particles that have energies above the threshold won't be captured. That should make you think that capture, which leads to a cascade, leads to lines. These are the low energy electrons, where a little bit higher, so they're not captured, deviation leads to thermal continuum. So I hope this answers the question now combined. The thermal process I talked about at the beginning of having just a deviation of the electron and emission. Those are the electrons that aren't captured. if you've got enough of those deviations, they will have lost enough energy that they will be captured. So these two processes occur simultaneously, as does their inverse. The ionization, the act of ionizing, is never precise. It's going to go to an energy always slightly above threshold, and the electrons can then lose energy by these continuum processes. You will see down to the depth from which that light can emerge, and no deeper.
Okay.
Now, the problem of astrophysical importance, of physical importance, is that the surface that you're seeing at any wavelength is never the center of the object. Even in the, well, no, this isn't exactly true. It's never the center of the object if it's opaque enough. In an ionized region, in a nebula, when you can see the central star, you're seeing completely through the gas.
Mm-hmm.
You can't see the center of the sun. In fact, the sun, oddly enough, is opaque at 1 solar radius.
By definition.
You can all laugh at that one. But 1 solar radius defined by the visible. And so this is another point that I hope will make it clear. When we talk about the radius of an object, we've chosen a wavelength at which to do the comparison.
Okay, that's a key piece.
And it's the same thing that all of you have been emphasizing in talking about calibrating spectra. You have to have a point of reference that everybody agrees to, because that which a cat will see in looking at Betelgeuse is not that which you will see. If you have a vampire bat who's accompanying you on your nighttime observations, and you're looking at an M star, that bat will tell you that its radius is a lot different than what you think it is. Okay?
Okay. All right, we've got 3 more questions, and I'm sure some people here are happy to stay with us till tomorrow. And
I do truly hope this is making sense to people.
Well, let's see.
Look, if it helps any
people are still here, still enthusiastic, and
okay.
It's good.
Steve, I want to go on to a question that that I know is going to be one of your favorites. What happens to the starlight between the time it leaves the star and gets to our telescope? And how does the interstellar medium, the ISM, affect what we see on our spectrograph?
The second is actually very easy. It's the reason we chose the title Dirty Window. I was amazed the publisher let us get away with that one. But you know the phrase, but now we see as through a glass starkly. When you look through a dirty medium, dirty meaning it has absorbers, and in particular the ISM, because it's literally full of aerosols. We don't know fully the origin of those particles, but we can actually hold them in our hot little hands. These are the so-called pre-solar grains that are embedded in meteorites. And they're also some of the material that's been accumulated in the formation of comets. And also, obviously, of the planets, but we just don't see that stuff. The ISM is populated in number by about 1 part in a million, with grains that can be as large as a micron in size. So, you know, about the size of a large virus or bacterium. Those locally are very, very rare. The ISM itself is exceedingly low density, only about a particle per cubic centimeter. compared with the air that you're currently breathing, that's about 20 orders of magnitude. And even astronomers note that, that's a difference. But when you've got path lengths that are parsecs or kiloparsecs, that very, very low density medium has a lot of obstacles to the passage of light. So the light can be absorbed, it can be deviated by scattering, it can be re-emitted in different portions of the spectrum. And that's entirely normal. It's whatever it is that produces the ISM, and it's the remnant of all of the star formation in the history of the galaxy, plus the contributions of the star formation in the galactic history. All of that medium has an effect on the passage of light. Now, the other question, the other part of the question is a little bit more subtle, and I hope people will bear with this explanation. If you're watching a baseball game or a calcio match, and the ball comes into the player, whether it's a batter or a fielder, and they either do a heady or they hit the ball is deviated. Okay, and somebody else can either scatter that ball, as in calcio or soccer, or they can catch it. Okay, that's the way we think of photons. Get this straight. Photons do not have a material existence in the sense of billiard balls or baseballs or calcio balls. We conceive of them that way because they're impulsive transfers of energy that have the same effect as being hit by something. But an absorption process destroys the photon. That photon, which is re-emitted by the atom after it de-excites, is not the same photon. It's simply that it went into an excited state, and whatever state the atom finds itself in, that's not the ground state, is inherently unstable. And so it decays, and it emits a photon. We call it a re-emission because it's easier to treat it that way. But that photon is distributed in space differently than the one that was incident. Now, okay, sorry.
It's a new emission and it can go in any direction.
In fact, it goes in statistically, it goes in all directions, but with different weightings. That depends on the transition. If it's a dipole, it's mainly forward or backward. If it's a quadrupole, then there's some that's going to go to the side. Basically, you can think of it like an antenna that, in fact, this is the easiest way to think of atomic absorption. It's basically an antenna that's resonant and that can re-emit. Okay, so it serves both as an absorber and a re-emitter, as a transmitter and an absorber. The transmission depends on the arrangement of the antenna. The absorption depends on the direction of incidence of the light. So in general, if you have the light incident in one direction, then hitting the atom, statistically, it's going to be spread over a larger range, and fewer photons are going to be emitted directly than the one that was originally coming. Okay? Statistically. And so you're going to see darkness at that wavelength. Now, if you see a photon at all, it's because it reached you. We used to have, when I was first with HST, and it was in the time of the Troubles, when the mirror was not quite ready for prime time. While we were figuring out what to do about the spherical aberration, a couple of us were joking that, just think of it, you have this poor bloody photon that's traversed a megaparsec of intergalactic space just to run into a spherically aberrated mirror. Okay? In other words, the photon that reaches you has had nothing happen to it. Nothing. If a photon reaches you between the time it was emitted and the time you see it, there was nothing that affected that. What you see, what you measure are not single photons. You see fluxes. That is, what fraction of the light that was emitted in your direction reaches you, not the fraction of a photon that reaches you. Photons don't subdivide. Okay?
Mhm.
Their energy can be redistributed among different emission mechanisms. But if you see a photon, if one actually makes it to you and registers on your instrument, nothing happened to it between the time it was emitted and the time you received it. The reason the intervening medium makes a difference is how it changes collectively the arrival of the light in different wavelength regions. Because the absorption of physical systems, because gas atoms, a gas consisting of atoms, molecules, or even solids, have characteristic spectra for absorption because they have internal structure. Those will modify the fraction of the transmission of the light, period. So the atmosphere has exactly the same effect as the interstellar medium. When you say that the X-rays don't make it through the Earth's atmosphere, well, they actually do. It's just there are so few of them, you can't register them. Okay, no medium is infinitely opaque. And statistically, it means that most of them are absorbed in the upper atmosphere at like 40 or 50 or 60 kilometers. If you take ozone as an absorber, light below about 3,000 angstroms basically doesn't make it to the ground. Of course, some of it does. There are few errant photons. It's a probabilistic process. But for the most part, the light doesn't make it through. Okay? What you're correcting for, either in calibrating a spectrum or recalibrating a spectrum using a standard, or simply taking a relative flux in different parts of the spectrum, is correcting for this differential transparency. Okay? I hope
Of our atmosphere, but that's
of our atmosphere. Now, the question of whether this can be done for the ISM, whether you can take a standard star and do for the interstellar medium what you're doing at the telescope every night for a comparison star, that's a harder question because we haven't recently visited any stars right next to us, you know? We haven't stood next to Vega. So we can't see Vega as we see the sun. But we can observe Vega and other stars that are very nearby, where we don't see the signature of the interference by the interstellar medium. The specific interference being absorption lines and bands.
Mm-hmm.
So if we take Vega, and this is one of the reasons we use it as the ultimate standard, if you compare stars with the same spectra, then presumably, and this is a big presumption, they're the same object. So if their colors are different, one of them, the standard, provides the correction for the other in the way the standard provides the correction seen through the Earth's atmosphere. The fundamental difference is we can go outside the atmosphere. We can't go outside the ISM. Okay? That's the real difficulty. The only way we can get around the interstellar problem is to take stars that are so near that they can serve as standard candles against which we can do the comparison. Otherwise, the only solution is find some very promising graduate student or PhD student and send them off with a little lamp that you've calibrated and tell them, okay, you've got about 50,000 years to do this project. We're going to send you to Alpha Centauri with that lamp, and you'll never make it to your doctorate defense, but at least we'll be able to measure that lamp as you're getting farther away. Okay, that's the real problem. The distances are so vast that we don't have the chance to do the kind of probing we would in the Earth's atmosphere. There's no problem with getting outside even of the solar system. It only took us 10, 30 years to do it. Okay, we've got the Voyager spacecraft now outside the solar system, but it's going to be literally hundreds of thousands of years before it's even remotely at a distance where we might see some effect of the spectrum on one of its signals. We just don't see that now.
Thank you, Steve. I want to cover two more questions. I want to see, we've still got a few people left with us. I want to go to a couple more practical things because a lot of people have asked me these questions, and so I want to get your take on this. So a gang of us have taken on the project of monitoring Z Andromeda, mostly with Alpi and Lisa spectrographs. One reason is to help us learn together how to improve the quality of our spectra, and the others for the potential scientific value. What would you suggest we be looking for in the spectra? What might be the open questions regarding symbiotic stars like Z Andromeda that low resolution spectrographs might be able to help answer? And I know one of the things you've talked about in the past in our conversations is time series. But what are your thoughts?
That's virtually everything.
Maybe
See,
you might.
all of you, let me make an emphatic point here. All of you have an advantage in what you're doing that those who rely on being able to get to large observatories or use large instruments don't. You are distributed all over the world on all different nights with somewhat similar instruments and somewhat similar detectors. The main thing is that you can sit on these objects for nights or months or years, and you don't have to be competing for access to the resources. There is one VLT. Okay, it's 4 telescopes, but there's one VLT, there's one ESO, there's one CFHT, there are 2 Keck. If you take the telescopes that are available now for competitive use in the range that would be useful for observing symbiotics at moderate or high resolution, there are a handful of them. Most of them have been shut down because they're not seen as front line. So if you get 2 nights on VLT in 3 years, you sacrifice a goat to the gods and thank them. Okay? You don't have a chance to sit there for a year and see what something is doing. If you can't do it in a couple of nights, or you can't do it in snapshots, the thought of continuously monitoring is impossible. Which is, in fact, something that all of you will have noticed, that the time series that are now available, which the AAVSO and the BAA and the New Zealand variable observers had been so famous and wonderful for being uniquely contributing, can only be done now because you have robotic telescopes. Okay, but robots have to be pre-programmed. They don't make the decisions for themselves, and so they're already prejudiced. unless they're doing discovery. Time series is not, doing monitoring is not new science. There's a whole area of astrophysics, astroparticles, who think they've suddenly discovered this new domain of the universe. It's called the time domain. I mean, this is complete crap. We've been doing time series since, easily since Tycho Brahe. Okay? It's the oldest thing to do in astronomy. You look at positions as a function of time. You look at brightness as a function of time. You may not think of the determination of the orbit of the comet of 1577 as a time series, but it was. And the only reason that anybody could do that was because they had access to the equipment continually. In Tycho's case, he built and paid for it. But in others, it was because at the Beijing Observatory, there were astronomers on staff, and that was what they were supposed to do. Okay? In the 20th century, there were observatory level projects that were done at, say, Mount Wilson by Olin Wilson, the monitoring of emission in the calcium lines of stars like the sun, that he carried out for 30 years. It's because of that that we know that there are stars like the sun that have sunspot cycles, because we see the cycling in the chromospheric lines. It's the same thing with the symbiotic stars. We know that some of them have Mira variables, not all of them. That is, they have long period variables of an intermediate mass that are red giants and that pulsate on timescales of order a year. Okay? You aren't going to get a year's worth of time on any modern large telescope to do the monitoring that might be necessary to understand those pulsations and to see, for example, how they time relative to, say, X-ray observations. The kinds of observations you can make with ALPI or with LISA or with LIRES are the kind of monitoring of changes that record the state of the system as it evolves. What we're looking for, let me say from my own bias, anything. To say that we understand a system well enough to predict its behavior is to say that system is no longer teaching us anything. Once we think we understand something, the aim should be to see how that understanding is incomplete. And the only way you can do that is to keep pushing. Once you think you understand something, you usually publish and then go away. You say it's no longer an interesting problem. And that only a dilettante or a crazy person is going to waste their time on something which is already well known. Most of the time that's true. But systems like symbiotics, especially, are always surprising us because we don't really understand the variety of physical processes. As with so much of modern astrophysics, the big picture in virtually every major area is pretty close to stationary. Okay, we know what a symbiotic is. We know how to describe it. We know what its components are. But the detailed microphysics of the accretion onto the compact object, the way that the mass transfers from the wind of the companion onto the white dwarf, the very process of accretion itself in those systems compared to symbiotics, compared to cataclysmics, so dwarf novae and novae, compared to X-ray binaries, as in low mass X-ray binaries where the gainer is a neutron star. We don't understand this. We don't in large part because we're used to looking at snapshots. And snapshots, when you take them on long time scale, give you the long time behavior, the average behavior of the system. Okay? Yeah, think of monitoring, forget the pandemic for a minute, monitoring the normal health of a population and the normal age distribution. Looked at in the big picture, you get the median, so you can take a census, say, every 10 years and talk about the state of the population. But you know that people are constantly getting sick and well. They're constantly being born and die. And so if you want to understand the birth and death process, it's kind of stupid to be sampling every 10 years. That's going to give you changes in the overall long-term behavior, but it's not going to tell you about the dynamical aspect of the population. It's the same thing with stars. A star like the Andromeda, for example, shows changes on decade timescales, years, minutes. It depends on how you observe it. And each one of those is linked to a different physical process or a different site. It takes days to weeks for mass to transfer between the stars. It takes years for the envelope of the red giant to adjust dynamically to its pulsations. It takes days for material to be incorporated into the boundary of the white dwarf. It may take seconds for the orbital time scale to produce very fine scale fluctuations in the brightness distribution around the white dwarf. All of those are going to contribute in different parts of the spectrum. The monitoring of the M star is mostly in the red and infrared, okay, where you're seeing it. The monitoring of the emission lines, on the other hand, is telling you what's going on in the vicinity of the gainer, of the white dwarf. Those that are the highest excitation, like the high ionization iron lines, those are coming from the inner region where it's exposed to very hard radiation. Not where it's hot, but simply it's close enough to the source, which is hot, that it's receiving far ultraviolet photons. Okay? If the source turns off, the disappearance of those lines is like looking at the way a light, once you've turned off the power, slowly diminishes in brightness. Okay, some of you will be familiar just from age with the really early televisions where you would turn them off and it would take a while for the tube to cool down. So you'd see this light in the center that would kind of diminish and disappear. Okay, that's basically what happens in symbiotics. What you're seeing in symbiotics is the emission lines from the environment, like a fluorescent light bulb, with the central source being the white dwarf that's being powered by accretion. Otherwise, the whole system would just turn off. Okay? So,
all right. Thank you, Steve.
Depending on which part of the spectrum you're monitoring, you're going to see different things. You have to learn, all of you, to ask the questions yourselves. If you decide, I'm really interested in what Myra variables do, go for it. Pick a bunch of Myras and then do a comparison with the ones that are in symbiotics and see whether you can find any differences. Whatever you produce, as long as it's consistent, reproducible, meaning all of the steps have been recorded, and reliable, it will be science. Okay? The thing that drives what you're looking for has got to be a question. You want to understand how something behaves, not simply you want to monitor it because it's nice to collect birds, or it's interesting to look at which trees you've got in which forests. If you're going to do physics, if you're going to understand the universe, which means you're going to do physics, you have to pose questions and then let nature give you the stuff with which to answer it. Therefore, the answer must be based on reliable information, which means reproducible data, accurate data for yourself, not just for the world.
Thank you, Steve. I want to go to some questions. We've still got an amazing number of people on here, 750 looks like. No, well, maybe not quite that many. I want to go to some questions that have come in here. Here's Patrick Kavanaugh. Some talks seem to give us answers. This talk gave us a different perspective to many ideas which we thought we understood. A perfect grab finale for this workshop. Okay, thank you, Patrick. I guess that was more of a statement.
Very kind. Thank you.
James Lay asked a very interesting question. He said, we had a great presentation today about SS4, I think it was 433.
SS433, yeah, we just did a paper on that.
Yeah, he says, can you talk about the ubiquity of disks and jets and how these scale with mass?
That gets a little bit, that's got to be divided among different types of objects. SS433 is an especially weird bugger because it's a very low mass black hole in a system with a very evolved star with an extremely strong wind. That is, it's an A supergiant with a low mass black hole around it. So let me make a more general statement. If you've got stars are big fuzzy things. Okay, again, keep that in mind. If you have them close enough together, they distort each other gravitationally. This is a tide. And if they happen to be still closer, then something happens that is actually inevitable. Let me just ask again, can you see the, are you seeing the yeah,
I'm seeing your tablet.
You're seeing the tablet, okay. So.
Yeah, we can see multiple pages and on one
yes,
side.
okay, so I have to go live here. Tapping, okay, right, so now you just see one, right?
Blank page.
Okay, so we'll start with the simplest picture. Take two stars that are sufficiently far apart. Then relative to the center of mass, which is just the center of mass, these stars are orbiting if they're not falling into each other. And they...
Well, are they not orbiting even if they are falling into each other?
Oh no, you can, if they have no angular momentum, they're just going to collapse radially. Okay, I'm assuming they have some finite angular momentum. Not that you simply, okay? When I say falling into each other, yes, in fact, they are in free fall, but they have angular momentum, so they miss each other. Okay, now, the reason for the tidal distortion is that relative to the center of the star, the material here doesn't have the right angular momentum that would correspond to its distance from the center of mass. And the resulting distortion that you get for this star because of the other one, and it's actually a mutual distortion, okay? That tide is because at the same time as this is falling, it's orbiting, okay? So this is being displaced inward and this being displaced outward relative to this. Okay, if these stars are close enough together, this distorts actually to the equivalent of a point. It becomes asymmetric and distorts to a structure like this, where now, remember, I said these were big fuzzy things. There's pressure inside of this, okay? This isn't a brick. And there's a pressure gradient because out here, there's nothing, okay? There's space out here. So all through this surface, we would normally expect that in equilibrium, this would be a nice balanced structure. But now at this point where it's critical, it is fundamentally unbalanced and material is literally forced to flow toward the companion. It has no choice. This is gas, which has essentially a puncture here, gravitationally speaking. The gravitational acceleration at this point is 0.
So this is sort of the Lagrange point, L2?
This is the Lagrange point. That's what it means. It's not the center of mass. That depends on the mass ratio. This is the point at which the gravitational acceleration locally in the orbital frame vanishes. And so material is forced to flow toward the companion because now the gravitational field is dominated by this mass. The result is, by the deviation because of the orbit, again, this has finite angular momentum. So it doesn't just fall straight, it orbits, collides with itself, and gradually circularizes. And that's what forms the disk.
Okay, but now what is the jet, the portion between the L2 point and that center of mass?
No, this is just a stream. It's the equivalent, as I said, of puncturing a balloon.
Okay.
Now, this is the part that gets difficult because, frankly, we don't know how it works. There's one thing we know. SS433 was the thing that actually showed us for the first time that this was true. That if we looked at this from the side, as it happens in SS433, the accretion actually produces a disk which isn't quite aligned. Now, the reason for that lack of alignment is that you have here a spinning object whose axis is not aligned to that of the orbit. Why? I don't know. That's a fact of the system. That the accretor is not, the orbital angular momentum of the accretor is not the same as the orbital angular momentum. Now, what happens in the inner portion? Because we know the flow that we see comes from that. It's a combination of several things. First, there's a flow off the disk. This is an evaporative flow. It's a wind. And we now know that. The disk is hot, it's viscous. It's dissipating energy. This isn't simply the flow in a bathtub where you've opened the drain and the stuff is going down. This material is moving at something like a tenth the speed of light by the time it gets into its inner portion. The collisions alone are going to generate a heating that raises the temperature to tens of millions of degrees. At that energy and with the luminosity, with the amount of energy that's being dissipated, it can drive a wind. It's a small thermally evaporative wind that just blows off the disk, but it's there. And the innermost portion appears to be the origin here of jets that are accelerated outward and eventually reach about 1/4 the speed of light. If you didn't have a black hole there, you wouldn't see these jets. In protostars like T Tauri stars, you see the same thing. It's just not relativistic. In T Tauris, it's a dense jet. It's a slow jet. It's only a couple of 1,000 kilometers or 100 kilometers per second. So 2 orders of magnitude slower. Nonetheless, It's a jet. And the principal reason for that is something you all know, that if you have, let's say, a disk, and so a carousel or anything that's rotating, and you attempt to walk from the center to the edge, you're going from zero angular momentum or just spin out to large angular momentum because you're increasing your radius. Okay? Now, if you're trying to stay on the disk, you appear to be subject to a force, to a torque. Okay? Because now you're trying to increase your angular momentum. That's the Coriolis. Okay? You can't walk outward radially, inward or outward, but you could walk around with no problem, right? Well, if you blow straight out the axis, then it's the same thing. Anything that moves material off the disk, anything that moves in this direction can do so more freely than if it tries to expand spherically. And so the system is auto-columnating in a way that the mirrors in a spectrograph would love to do, you know? This is axisymmetric. The thing that's remarkable about SS433 is it's close enough that we can actually resolve some of this spatially. And that this disk, like a top, because it's in the presence of this gravitational field, the disk itself precesses. It flops. The easiest way to imagine that, I don't have a good film of it, but if any of you have ever watched in a pizzeria, one of the cooks, one of the pizza chefs making the pizza, they spin it around, okay, on their fingers, and it's flopping. It's not rotating like a disc. There's a wave that moves around inside the pasta, okay? That's basically what's happening here. That there's a differential precession of the outer part and the inner part. The inner part is aligned with the axis of the black hole, and the outer part isn't. And that's what's creating the precession. So the SS433 itself, the system, was originally found because it had a really strange spectrum in the optical. And any of you who have ever looked at it will find it really kind of weird. That there are the stationary lines, which are from the ordinary binary and disk. And then there are these lines that change their positions by hundreds of angstroms over the course of about 164 days. The so-called moving lines that I'm sure Blundell described in her talk.
Yeah, she did.
The moving lines are formed from a kind of intermediate part of this jet, where the gas has sufficient emission measure and sufficient recombination that you can actually see the lines in the optical. The base is visible only in the X-rays. It's not a strong gamma source. It's not a strong TeV. It's not seen in TeV energies. It's actually very appropriate. If I'll just say something personal, Nick Sandulik, who was one of the S's, and Bruce Stevenson, who was the other S, had offices on either side of mine, or rather I was in the middle of their offices in the first faculty position that I held at Case Western Reserve, the Warner and Swayze Observatory. So I knew these guys when the source was already famous, and had been studying it actually by accident before Nick and I ever met. The reason this thing was picked out was not because it was unusual in any other characteristic. It was just on a list of stars that hadn't been included in other catalogs that these guys had done of emission line objects because they couldn't figure out what the lines were. Very, very low resolution. You look, this actually should give all of you encouragement. The original observations were at a resolution of like 100. Okay, 120.
So Lauren can get this with her drift scanning technique.
Yep.
Fantastic.
No, this is SS433 and the very few systems like it, the so-called microquasars, because they look like quasars, or they're like what we think quasars should look like. Those systems can be studied at very low resolution and still get information that's important. Again, the most important thing here is knowing how the source varies. I don't mean this as publicity, but one of my students who has been at Haute-Provence and so has met some of you, Paolo Picchi, and I just did a paper this year doing the high dispersion work on the system and trying finally to put all of the stuff together about the stationary lines. So everything I've said about the state of the system itself is based on Paolo's thesis. And the paper that we had come out in the fall. No, actually it was in the summer. But that was largely based on resolutions of greater than 20,000, because you need that to study the details of the accretion process. But if that's only a part of the picture, okay? So the gross behavior of SS433 can be understood by even low resolution, provided you have the time series. Now, okay, the system goes through hiccups. Like all mass exchanging systems, it is not perfectly stable. Okay? It has a very strong, unpredictable element. It blows material out. The jets don't have the same brightness all the time. It can go into outburst. There's a very beautiful paper by Blundell and colleagues from almost 8 years ago now that studied one of these outbursts in beautiful detail and showed what kinds of changes can occur in the line profiles. And they were using moderate resolution for that sort of study. We had used the Liverpool telescope, and by sheer chance, we were observing it for polarization. But by chance, the system went through an instability. Disks are unstable for a very simple reason. They radiate. And if the densities change and the opacities change, their structure changes because they're building themselves in a gravitational field with internal pressure balance in response to this rate of energy dissipation. If I could give you any more answer than that with any certainty, I'd be very happy and maybe you'd be satisfied. But we don't know the rest of it. As I said before, this is the big picture. That we know. For this system and for others like it. We know very well the gross behavior, but the devil is in the details here. How does the material actually get through the disk? The transfer isn't that you're going directly into the central part, that the material isn't falling in somehow like it does in a bathtub. It's a much more complicated process that transfers the material inward. That has to involve the equivalent of friction. It has to involve viscosity. Something's got to slow the material down for it to fall in. And yet, and this has been the problem remaining in accretion theory for the last 50 years, we still don't have the full complement of mechanisms that give us this viscosity. It can't be the same in all systems. They don't look all that universal, and yet they have one universal characteristic. They look like they have viscosity. There are technical problems connected with where that comes from, what the role of things like magnetic fields are, or the roles of magnetic fields, and what cooling and heating processes are available. But those vary from environments. The basic picture of a disk is that material is fed from the outside, gradually drifts inward, ultimately accretes on the central object, and because that's deep in a gravitational field, it gets very hot and can puff up or even blow out, or accrete and give rise to explosions, as happens in novae, or perhaps never even accrete, just reside in the disk for a while and then get blown out. All of those possibilities are there. Symbiotics, in that sense, connect directly with SS433, which connect directly with dwarf novae, which connect directly, perhaps, with quasars. Accretion, gravitation-driven accretion has no fixed characteristic scale. So the other reason for studying systems like SS433, one of the motivations, I think, for the Oxford group, and for others who have studied this, is that we can pass as a model in a gross way from this system to, say, the quasars or the radio galaxies that have these 100 kiloparsec long jets. But it is not precisely the same phenomenon. In the change of scale, things happen. In the way the system is fed, things happen that are different in these systems. So the other reason for studying them is to do a compare and contrast. By seeing those differences, we learn something fundamental, where we could say, well, if we understand SS433 or GRS 1915, great, we understand the quasars. Okay, and then we go home and think we understand the quasars. Well, we don't, because quasars aren't fed by an external source that's in a bound system. They're not binaries. That does seem to play a role. It structures the outer part of the disk. It may structure the way the material is supplied to the disk. So the phenomenon, the basic phenomenon of accretion leading to disks and jets, that appears ubiquitous. Get the material falling onto the star, make the central object compact enough that the energy released in the fall can heat the gas or energize the gas to the point where some of it can actually escape along the axis of the system. Yes, that's universal. We see it in binary protostars. We see it in accreting protostars. We certainly had things like this in the early history of the sun and the solar system. It happens in novae, in cataclysmics, in algal binaries. It's everywhere. It is ubiquitous, but it's not universal. It happens at different stages in life of stars, and in that may manifest itself differently. And that's the sort of thing, again, that requires time series. If you take a snapshot of SS433, you would never know what the damn thing was. Okay, you observe it with the wrong cadence, and you wouldn't figure it out. Which was exactly why it was called the peculiar object to begin with. There were only two spectra. They had been taken a couple of years apart in a survey, and they didn't look quite alike. But neither Nick nor Bruce could figure out what the lines were. So they put it in a list of objects that were peculiar. And it was then picked up as an X-ray source. And Bruce Mygon happened to know that, amazingly, happened to know of this paper, because this was in the days before the ADS and before Simbad and before the CBS. And there it was, number 433 in a list of stars from the 1970s.
We're getting feedback from your microphone again.
Oh, okay. So, sorry. So that's the way it was discovered. And that's the sort of thing that would easily be within the range of any of your instruments.
That's music to our ears, Steve. I think that 62 people have held on here to this conversation, hoping to hear that what they're doing is potentially of value to the scientific community. And
oh, I can tell you with a source like this, anything that you produce in a systematic time series in the course of a couple of years, that is, say, 2 or 3 observing seasons, is going to be invaluable, not just valuable. If it makes if it gives you any inspiration, people, all of you, I happen in this study with Paolo, we used the same data that had gone into the paper that described the outburst. It was data that had been taken with the NTT at AAVSO, but this was data from more than 10 years ago. It had been used for one purpose by Blundell and her collaborators. We used it for a completely different purpose. It was the same spectrum. It was, in fact, a series of some 60 spectra that had been taken over a span of a few weeks. We then had data that had been taken at AAVSO and also some of our own data that spanned between them first years and then decade. Okay, and between those, we were able to separate out the different kinds of and different time scales for the variability. Okay, but most of the data that we were using was taken for another purpose by somebody else, but it was reliable and we could check the reliability. Okay, so anything you do, anything can have permanent archival value. The phrase that just came to mind is one from Julius Caesar when the conspirators have successfully carried out the assassination, and they're standing around trying to figure out how they're going to, what they're going to do next. And Cassius, the brains behind the conspiracy, says to the rest of them, how many times will this our lofty scene be acted o'er, in states unborn and accents yet unknown? How many times shall Caesar bleed in sport, that now at Pompey's base lies alone no worthier than the dust? The point is, how many times will this be reenacted? We don't know. In states unborn and accents yet unknown, in projects directed completely differently than the ones for which we were originally taking these data. You don't know. We're the only field that can say that, you know that, except for geology or ecology. We have we have the historical side. The universe is never the same, and neither are these objects. There's no object in the universe that doesn't change. The only question is on what scale and what magnitude, and whether we can see it and what do we learn from it. Okay.
Thank you, Steve. I want to pick up just 2 more questions, I think, here that see, and this may go back to your stadium drawing. Gregory Donahue has asked, bound states, electrons moving to a higher shell.
Yeah.
Does the photon creating the transition have to be the exact energy to make the transition, or can it be at or above the required energy of the transition?
The answer is yes. It can be either. If it's above or below, then it's not resonant, and so that's like Raman scattering or Rayleigh scattering. But Raman would be where you absorb out of the exact transition, but very near it, and provoke a transition. So in other words, you could be damn near the seat, but you could go slightly above the row and sort of overshoot and then fall back. That's a very crude way of looking at it.
What's the term for that?
Raman.
And falling back?
That is, you're not resonant capturing, but you're not far from resonance. And so the process, which is actually also used in the laboratory as a way of analyzing chemicals, is fluorescent. So instead of it being, can you see the screen?
Yes.
It's not this precise transition, it's that this may be excited in a range here, because having a finite lifetime, if this is the ground state and the other is an excited state, then anywhere in this interval of energy, an absorption is possible. Okay, but it's also possible that two lines can be very close, so you could have actually a line transition here going to a state here. Okay, this is Raman.
And so that's responsible for the Raman lines that we see in some spectra.
That's right. The most famous example in astrophysics is the identification of the 6825 7083 lines, which are oxygen 6. And the reason you see those is that this line with the broad wing, is Lyman beta, and this is a pair of lines in 06 that by just chance lie at 1038 and 1042 angstroms, where Lyman beta is at 1026 angstroms. So these are just almost resonant with Lyman beta, and the difference in the energy between these is what you see as these lines. Now, this requires that you have an emitter. I think Francois would have explained this, that here you have a light source which is producing the 5 times ionized oxygen lines, and you have a converter out here in cold gas. So these lines get absorbed and scattered. And what you're seeing are, I'll call them the 06 R lines. But this absorption is because out here you have neutral hydrogen. If you didn't have this source surrounded by enough neutral gas, you wouldn't see these lines. Strip that gas away and you won't know that there's a hot source there from looking at those lines. Okay? Mm-hmm. The same thing can happen with any neutral absorber. Helium is perfectly capable of producing Raman lines as well. It's simply not as abundant. This happens to be the most abundant species in the atmosphere of the giant companion that's surrounding the system. So remember that what you have here is a wind, the red giant in the center, and then next to it, you have this accreting system, which is creating around it a kind of planetary nebula. So this gas is the emitting gas. This is the accreting white dwarf. So this is the ionized wind, which actually looks more like this. And then whatever light is emitted from here, some of that can scatter toward you in these lines. If the source, if the white dwarf is too cool, it doesn't create the O6. You don't see the Raman lines. If the source is surrounded by medium that's too ionized, then by the time you reach the neutral gas, you can't excite it. Okay? There just isn't enough there of the photons. So again, you don't see the Raman lines.
So these Raman lines, in some sense, a temperature indicator of the white dwarf?
It's a continuum indicator. And so, yeah, for a white dwarf, you could say that's a temperature indicator. If you don't see the lines, it's not definitive. If you do see the lines, then it's definitive.
Okay.
Hi, Steve and Woody. I'm just trying to. Well, this is a wonderful discussion. I just want to tell you that there is a lot more and more people who are leaving the meeting because I think it's difficult to be concentrated, and we have overpassed the planning for a long time.
I guess we actually have gone kind of really.
I never succeeded to stop you because this is a good experiment, because if we don't stop you, you never stop, in fact. Well, I'm kidding. I'm kidding. Anyway, so if you can just finish in a few minutes.
But wait, I have an excuse. I'm teaching now in Pisa, and Galileo was in Pisa, and inertia was discovered in Pisa.
Yeah.
Okay. So right now, of course, I'm in Geneva, so it doesn't apply quite as directly, but.
No. Anyway, well, still a few minutes, so finish what you are saying. But I think now it's now time to have a stop.
Okay. No, the only point I wanted to make is perhaps to emphasize what I think Francois would have said when Tessier was explaining the spectrum of these stars. The ionization that you see and the lines that you see should never be interpreted as temperature. It's not that simple. It should be interpreted as emission in that part of the spectrum that can produce the lines that you see. Okay? There are lots of ways of getting X-ray emission without making a medium hot. There are lots of ways of producing large ionization differences without necessarily having a hot source. And a UV continuum isn't a measure in an absolute sense of temperature. Some of you will have heard, I've ranted about this in other contexts, the terms Ijima temperature and Zanstra temperature. Those are just ways of measuring how strong the UV and EUV, extreme ultraviolet, are in the spectrum distribution. They are not uniquely temperatures. The best example I can give you is you put the white dwarf. Take these two cases. You have the white dwarf surrounded by material, okay? Or the white dwarf surrounded by very much less material. Okay, so this ionized region is exactly the same between the two of them, except this is like a planetary nebula, and this is the wind of the M star. Okay, this source is not going to show the Raman line. This will. This doesn't have the path length to produce the Raman emission. It's the same star. You just change the environment. Okay? The Zanstra temperature and the Ijima temperature and any other temperature is just a measure of conversion efficiency. If you have the source isolated, you won't see it because most of its radiation is coming out of the optical band. Okay? You wouldn't even know it was there. And that's why these things were called symbiotics in the first place, because you saw you saw the spectrum of the late type star, but superimposed on it were lines of helium-2, which couldn't possibly be coming from that. It's also why for a long time there was a controversy in a small community that wanted to explain everything in the symbiotics by a corona, which is, well, in the end, we know it's nonsense. But that's because we finally could see the ultraviolet when the first satellites were built to look in the UV. But the brilliance of Cecilia Payne-Koposchkin and Paul Merrill's understanding, the thing that gave the name symbiotic, was just this brilliant realization that there was another way of producing a composite spectrum. You make this a composite object. Instead of forcing the thing to be a single self-consistent structure, you just put something else there and you made sure you couldn't see it directly. But you predicted that it should be visible in the UV, for example. Same thing with X-rays. The reason for thinking that there were black holes in the centers of active galaxies was because there were indicators of things that looked like X-ray sources. Except we didn't have X-rays yet. When we had X-rays, lo and behold, these things were X-ray sources. In fact, they were all X-ray sources, even if they weren't radio. Okay? So what spectroscopy allows you to do is also probe parts of the spectrum you can't otherwise see because you're seeing the medium converting the photons for you. I'll remind you that every one of you knows the term fluorescent light, even if the current generation doesn't have to use them anymore because they have halogen lamps. But the way a fluorescent works is the gas radiates in the UV inside the tube and excites emission from a phosphor in the optical. When you're doing geologic analysis and you take UV light, otherwise known as black light, and you shine it on a mineral sample in the dark, and you look at the emission from the sample, that's fluorescent. That's a conversion process. Okay? That's the same thing as a symbiotic. What you see in the emission lines is a conversion process. So while you can't, looking at the lamp, you know, if you have a UV lamp and you hold it up to your eyes, you're barely going to see that there's something there, but you'll see an intense glow when you shine it on the right minerals. Okay, like fluorine or phosphor, or phosphorus. Okay. This isn't surprising. It's because the photons in the UV provoke emission in the optical. And the Raman process is like that. And any fluorescent process is a conversion process like that. You irradiate it at high energy, it re-radiates in groups of lines at lower energy. But it requires a sufficient opacity to be an efficient converter. And in symbiotics, it appears that we have enough of a converter. That was the other clue, that the lines that we see vary differently. So there are different positions in the wind. And from that and time series, we can do three-dimensional mapping, since these are orbits. They're big orbits and their path lengths change. Look, it's the same as a transit, or if you have Jupiter, it can't happen from the Earth, but you could imagine being on Pluto and watching an eclipse by Jupiter, where Jupiter moves in front of the sun, as seen from you or a spacecraft out at Pluto. Okay? The more extended the atmosphere, the longer the eclipse is going to last, and the deeper you can probe the atmosphere. When you see a sunset on the Earth, you're doing the same thing. You're getting a three-dimensional picture of the atmosphere. You're tracing the path of the light from the sun as it goes through the atmospheric layer. And you can do that spectroscopically as well as photometrically. The beauty is spectroscopically, you can separate all of the contributors. So you can see where in the atmosphere the water layer is, or where in the atmosphere there's ice, or where there might be an ozone layer, because you can separate the spectra. Or thinking of global warming, where there are fluorocarbons. Okay. Oop. So I have the feeling that people are probably climbing the walls by now. I don't mean to be keeping you all, but.
Well, Steve, I think everybody really enjoyed it, learned a lot from it. I've seen
I'm always available. Anybody who feels like writing, just feel free to do it. I actually work your hours.
I know that.
So I would be delighted in any clarifications, comments, or questions, or whatever, always.
Well, thank you, Steve. And, you know, on behalf of the people out there who can't really speak at the moment, I'm sure they're saying thank you as well. And I would encourage them to take you up on your offer. This is a great way, I think, to finish up this workshop. We kind of started out with astrophysics. We're finishing up with astrophysics, and it was a perfect opportunity for people to get a chance to ask their questions and get answers. And I appreciate your effort. I appreciate Woody's effort. And I guess at this point, it's time to say goodbye for the time being. But like I said earlier, there will be more events sponsored by the AAVSO. The AAVSO is very committed to working with small telescope spectroscopists. And so thank you, everyone. We'll have more events in the future. And like I said, we're really hoping that we can have an in-person event in the Boston area next November. So thank you very much. And you'll hear from us soon. Bye.
Thank you. Thank you. Thank you to all. Thank you, Steve. Thank you, Woody.
You're welcome.
Thank you, guys.
Bye,
Thank
Steve.
you.
Bye, Francois. Bye.
Bye, Woody.
And
Thank
we'll
you.
be in touch soon. Good night.
Ciao.